The following message is best viewed on an oscilloscope.
Okay, I guess that was the introduction. Okay, I haven't seen that before. Well, welcome everybody to ICHEP 2020. It's a very unusual format. I'm Petra Merkel from Fermilab. I'm your host today for this first session of the Detectors for Future Applications. And today's section is actually exclusively about upgrades for the LHC. So both phase 1 and phase 2, mostly phase 2. And I would like to ask every speaker if they can to share their own slides and use maybe the cursor to point along, and also share their video if their bandwidth allows, so we can at least see the speaker. And all the talks today are 15 minutes, which is 12 minutes for the talks plus 3 minutes for questions. And after 10 minutes, I will give you a 2-minute warning for the talk. And then if you have questions, please keep them for the end of each talk and raise your hand. I hope everybody knows how to raise their hand in Zoom, and then I will try my best to call on you. Okay, and that said, we can start with our first speaker today, which is Katja Klein from Aachen University, talking about the tracker upgrade in CMS.
So, thank you. Hello, everybody. So I will talk about the CMS tracker upgrade for the high luminosity LHC. And I will start with a short overview. So we will install a new silicon tracker in long shutdown 3. It has an outer tracker that replaces our strip tracker and an inner tracker that will replace our phase 1 silicon pixel detector that was installed in 2017. The main design goals include to be capable with the high expected data rates, radiation tolerance up to the required fluence and dose levels, increased granularity, tracking acceptance up to eta equal 4, and we'd like to contribute data to the level 1 trigger. So you see here that we have a relatively classical barrel end cap design with inclined modules in the inner part of the outer tracker. So the yellow and green lines symbolize our pixel modules with 100 times 25 micrometer squared pixels. Then in blue, we have the pixel strip or PS modules with 2.4 centimeter long strips and 1.5 millimeter macropixels. And further outside in red, we have the strip or 2S modules with 5 centimeter long strips. So I will start with the outer tracker. Here, the design driver is to use tracking information at the level 1 trigger. Presently, we use there only muon and calorimeter information, so the provision of tracking information will clearly enhance our performance. However, we cannot read out the complete detector information at 40 megahertz, so we have to reduce the data volume already at the front end, and for this we exploit that the vast majority of the hits are from very low PT tracks. So for the level 1 trigger, we select hits from tracks with a PT above a certain threshold. So in the sketch, you see a cross section through one module. We have 2 sensors on top of each other, spaced by a few millimeters. And the tracks leave hit patterns there that depend on the bending in our very strong magnetic field, and thus, of course, on the PT. So to the level 1 trigger, we send stubs, which are 2 hit tracklets from high PT tracks at 40 megahertz, where the tracks are then reconstructed and the level 1 trigger decision is formed. Once we receive a level 1 trigger, of course, the complete event information is read out. So how is this realized? Here you see how our modules look like. So on the left, we have the 2S module with 2 strip sensors on top of each other with 5 centimeter long strips. They are wire bonded to the front-end hybrids, which carry the readout ASICs and a concentrator ASIC. And then we have a service hybrid that is responsible for the power distribution, data serialization, and optoelectrical conversion. In the PS module on the right, we have a strip sensor on top with 2.4 centimeter long strips, and below that a macropixel sensor with the 1.5 millimeter macropixels. So the strips are wire bonded to the front-end hybrids, which carry another readout ASIC and a concentrator, while the macropixels are bump bonded to a third readout ASIC below. And then we have a power hybrid and a readout hybrid. So electrically, the basic building block is the module. We do not have any common service boards in the auto tracker. So the module is a self-contained unit carrying all its services with it. So for the silicon sensors, we have 3 types: 2S, PS strip, and PS macropixel. All designs are final. We will use planar N1P sensors from float zone silicon with 290 micrometer active thickness. We have investigated many different options, but this is the outcome of this campaign. So in particular, we have done years of irradiation and annealing campaigns. And basically, I show here the quintessence of this. So the plots show the seed signal versus annealing on the left for 2S sensors and on the right for PS, where the sensors were irradiated to significant levels, which cover the vast majority of the modules in the tracker, as you can see from the distribution on the left. So the blue points are the relevant points here. And you can see that we have a signal above our requirement, which is 3 times the threshold for 600 volts for 2S sensors and 800 volts for PS sensors. So the sensors are all ordered. They will all come from one supplier. And at the moment, the pre-series sensors are arriving, and but we have to test them. Now, in terms of electronics, I will concentrate on the 2S module as an example. So we have this relatively complex front-end hybrids that carry 8 CPC readout chips and 1 concentrator. So they are 4-layer flex boards with a carbon fiber stiffener, a high line density, and a tight fold over. So you see here a sketch on the right. It's a cross section. The hybrid is the green part. So the strips from the bottom sensor are wire bonded to the bottom side of the flex, and then the signals are routed through the fold over to the top side where the chips are sitting. So our readout chip is the CMS binary chip. It features unspecified binary readout at 320 megahertz, reads the signals from the 2 sensors, correlates the hit patterns, and thus finds the stubs. Then we have the concentrator. It's a digital chip in 65 nanometer. It receives the data from the CPCs via 48 lines, formats them, and sends the data further to the low power GBT, which sits on the service hybrid. So the LPGBT receives the data from the CRCs and ships them further to the VTRX Plus at 5 gigabits per second. The VTRX Plus does the optoelectrical conversion. And then we use a 2-step DC-DC conversion powering scheme with the CERN DC-DC ASICs. So the CBC is in mass production, and final prototypes of the hybrids are currently being ordered. So up to now, we have built of the order of 20 functional modules of various generations. This allowed us to exercise the complete readout chain in various system and beam tests. So for example, the noise is below 1,000 electrons as specified. The plot here shows a comparison of the noise with optical readout and DC-DC converters as compared to electrical readout using a lab power supply. We have exercised the stub mechanism in beam. So the plot here shows the stub efficiency versus emulated PT, which is achieved by rotating the modules in the beam. And you see that both for a non-irradiated and an irradiated module, a high efficiency of the order of 98% is achieved, and the PT resolution is of the order of 5%. The modules are mounted on carbon fiber and foam support structures. So in the 2S barrel, we have these ladders. In the PS barrel, we have plunks and rings in the flat and tilted sections respectively. And in the end cap, we have these very large Ds, which carry PS and 2S modules, and 4 Ds form a double disc. So at the moment, we are building prototypes and cable mock-up to study mechanical aspect and the routing of the wires and the fibers, which is challenging. We're going to use two-phase CO2 cooling at -35 degrees, which allows us to move to thin pipes, which is advantageous for the material budget. A challenge is that the modules are relatively power hungry with 10 watts for the PS modules, so thermal management is crucial. The 2S modules will be screwed to the pipes via 5 inserts, while the PS modules will be glued over the full area with phase change material. So moving on to the inner tracker already. So we will have a 4-layer barrel accompanied by 8 small and 4 large discs. The challenge here is, of course, the high fluence in those levels, in particular in the innermost layers. Therefore, we have this half shell design that allows us to relatively easily extract the detector with the beam pipe in place during standard shutdowns. And we have this feature already now. The modules will have 2 or 4 readout chips. These are hybrid pixel modules, so meaning that the sensor is BAM bonded to the rocks and the high density interconnect is glued on top of the sensor and wire bonded to the rocks. The HDI is responsible for power distribution and signal routing. The rock is based on the RD53 ATLAS and CMS development for a pixel chip in 65 nanometers, and it has to cope with very high hit rates. So in terms of the sensors, the baseline for us is to use planar sensors. 3D sensors are an option for the innermost layer. In fact, we consider to replace the inner layers after, for example, half of the lifetime. The sensors will be NNP with 150 micrometer active thickness, and the baseline pixel cell is 100 times 25 micrometers squared. So here in these plots, you see test beam measurements. The efficiency is plotted versus the bias voltage for planar sensors on the left and 3D on the right for various levels of radiation. And the bottom line is that we can achieve 99% efficiency for 50% of the layer 1 fluence, for 450 volts for planar sensors, and already for 150 volts for 3D sensors. Of course, this is one of the big advantages of 3D. The last plot shows the spatial resolution as measured in the test beam versus the turn angle, so you see that the resolution is excellent. So coming to the electronics, the CMS ROC is developed as a variant of the RD53B chip we want to submit end of this year. We are using the linear front end and the slightly different pixel area as compared to ATLAS. The chip has a binary readout plus a time over threshold feature and a shunt LDO for serial powering. Of course, it will be very important to do the full radiation qualification of the RD53B chip. Yes, we are using...
2-minute warning.
Thank you. We are going to use serial powering, which allows us to move to a low material budget in spite of the 50 kilowatts of front-end power that we have. So we will have up to 12 modules in a serial powering chain, where actually the chips in a module are connected in parallel and the high voltage is distributed independently in parallel to the modules. So we've exercised this with chains up to 3 modules, and the figure here shows the noise difference between serially powered modules and individually powered modules. So this looks fine. The modules are then connected with up to 1.6 meter electrical links to port cards that sit at the periphery of the detector. A port card features 2 LPGBTs and 2 VTX pluses for the readout. And here we use, again, a 2-step DC-DC conversion scheme similar to the outer tracker. The communication is AC coupled, of course, because of serial powering. Okay, a few words on the performance. So we're going to have a high efficiency and a few % fake rate for TD bar events at 200 pile up. As an example, I show the efficiency here versus ETA. So in fact, the performance will be similar to the phase 1 tracker at a pile up of 70. So in the middle and on the right, I show the transverse momentum and transverse impact parameter resolutions for muons as compared to the phase 1 tracker. So you see the bigger acceptance and the better resolution. Finally, for the level 1 trigger tracks, we also have very good performance. So I picked here a plot showing the Z resolution, where you can see that we can achieve in the center of the detector resolution of the order of 1 millimeter at 200 pile up due to our macro pixels. So this is very, very useful to mitigate pile up, of course. Okay, so to conclude, you've seen that the design requirement to deliver tracking information at level 1 leads to an innovative but also challenging detector design. The project is in good shape and we are so far on track. The outer tracker project is in the prototyping phase, with first items now entering pre-production, like the sensors or the readout chip, while the inner tracker project is entering prototyping. So the new tracker will surpass the performance of our current tracker under much harsher conditions. And we think that the physics output will be boosted also by the capability to trigger on tracks at the first trigger level. Thank you very much for your attention.
Great, thank you, Katja. Okay, I see a question. Andreas.
Hi, you hear me?
Yeah, I hear you.
Very nice. Well, you can also see me now, but I'm concerned.
Yeah, I see you. Hi.
Hi, very nice. I have a question for the, as you said, there's a binary readout with TOT capability. Is your baseline to read the pixels binary, or are you planning to read out TOT information?
I'm probably not the expert on this, but I think the baseline is to read out binary. So I'm not sure for what exactly we are going to exploit the time over threshold feature actually.
I'm asking because in the past, ATLAS has at least benefited a lot from having a dedicated cluster splitting in place, which uses, so for very dense jetty environments that uses the TOT information. And of course, since you're using the same RD53 baseline, I was wondering where you're swinging to this. It's a trade-off, of course, I'm aware, yeah? Okay.
No, I'm sorry, I...
No worries.
Yeah.
Okay, are there any more questions for Katja? If not, thank you again. Very nice talk. So we can move to the next one. This is Stefano Terzo from Barcelona, talking about the phase 2 upgrade of the ITK pixels.
Yes, here I am. So let's share. So I guess you see now.
Yes.
Okay, so I can start. So I will give an overview of the phase 2 ATLAS upgrade of the pixel detector for the Luminosity LHC. So, okay. So here you see the timeline of the LHC accelerator. So we are now in this long shutdown 2, and the pixel detector of ATLAS already had an upgrade in long shutdown 1 around 2013, 2014, where an additional layer was inserted for ATLAS, was the fourth pixel layer, very close to the beamline. And we took data in RAM 2, where we had like this situation that you see here as a pileup, which also with much higher luminosity with respect to the nominal one that we were able to reach was about 55 pileup events. And when we will go now in phase 2 after the long shutdown 3, the end of around in the middle of 2027. We will instead be in this situation with a pile-up level of the order of 140, 200 pile-up events. And ATLAS, because of this, ATLAS foresees to exchange the inner tracker completely with a full new inner detector, completely made of silicon with 5 pixel layers. And there are two major challenges for this new inner tracker, which are the high particle multiplicity and the critical radiation damage. you can see here what I'm talking about. So the particle multiplicity will be about 10 times more. So the tracker density will be 10 times more. This means that we will need a much better tracking granularity, and we will have to cope with the increase in readout rates. And also the radiation damage will be critical. We can see here the total ionizing dose as we get closer to the beam pipe, here to the innermost pixel layers, and the same for the equivalent neutron fluence. So the radiation dose will become critical, and the total ionizing dose will be up to 10 megagray, and the particle fluence up to 2 times 10 to the 16 in the innermost pixel region. So the present inner detector piston will be replaced with a full silicon inner tracker, which will have to maintain, even improve the present tracker performance in this harsh environment, keeping the low occupancy less than 1%, minimizing the material, and facing these new radiation challenges. So you can see here a layout, a sketch of the future ITK. So in blue, here you have the strips. You have 4 strips barrel layers and 6 end caps per side. So you will hear more in the next talk about the strip detector. And here instead in red, the pixel detector, which will have 5 layers, 5 barrel layers, and pixel rings with also this inclined solution in the outer layers. So the coverage will be up to 4 eta, and this structure with rings will allow to have at least 9 space points per tracks. Also because of the very high radiation levels in the innermost layers, the 2 innermost layers will be replaceable. This will allow to reduce the radiation damage. But also the area compared to the current pixel system, you will see it's huge. So we can see here, zoom in the pixel system here, where you see here, for example, how these in this outer layer, the barrel and the rings will be designed on the support, and have these instead internal rings. And for example, for the layer 1 and layer 0 will be implemented mechanically. So in the outer barrel and forward pixel, there will be an NMP planar silicon sensor, 100 micrometer thickness, active thickness, in a form of quad modules. And you can see here the number of quad modules is very large. So here the focus is in having like a solution to cover this large area. In the inner pixel layers, instead, this will be replaceable, and there will be thin NMP planar silicon sensor, 100 micrometer thick active thickness, also in the form of quad module for the second layer. And the innermost layer instead will have 3D silicon sensor, which will be not in the form of quad module, but in the form of pseudo triplet modules. And this will be as close as 34 millimeters from the beamline. So I mentioned the material budget. This will be much reduced with respect to the current one in Run 2. You can see here on the left what we have in Run 2, and this line gives you an idea of how much it will be reduced as from simulation of the ITK layout. This is thanks to the evaporative CO2 cooling system, which will be used to cool the modules, which is used titanium beam pipes, and carbon structure for mechanical stability and mounting. And also there will be an optimized number of relay cables using link sharing. And all this especially will profit from the use of serial powering. So the serial powering scheme that use shunt LDO, which allow voltage regulation with constant current from the external power source, with an average chain of about 10 modules. This will reduce the number of cables. So what is this here? There is some sketch of how these serial powering will be done. So the low voltage inside the module is distributed in parallel, here for a quad module, here for a triplet, for example, while we will have several HV line for each serial powering chain. Let's talk now about the module. So the part of the front-end chip, presently we had like most of our results with the RD53A, which was first a large prototype in 65 nanometer. Common ATLAS and CMS R&D with already small pixel size, 50 micrometer, which had 3 different analog front-end implemented. and also ready Chantal DO regulators for serial powerings. So ATLAS selected differential front end to then build the full-size chip, the first ITK PIX V1, which has been now produced in 65 nanometer technology. The radiation hardness is foreseen to be more than 5 megagray, and also in time threshold less than 1 kiloelectron, high trigger rates and heat rates. So also indeed, with respect to the 53A design, there is improved Chantal DO for serial powering and data format, including compression and forward. So here the news is that the first ITK PIX V1 chips are ready for module assembly. They've been produced. So in the outer layer, there will be planar sensors. So with respect to what we had now in IBL, which are 200 micrometer N-in-N planar sensor with 50 by 250 micrometer pixel cell, ITK we use NMP technology with a single side process with 50 by 50 micrometer pixel cells. So this will be 150 micrometer for the outer layers and 100 micrometer for layer 1. So the active thickness is chosen to ensure the larger radiation hardness when we go closer to the beam. So the performance required that have been measured are more than 97%. We require more than 97% heat efficiency, and this was obtained at the end of life. So for the highest radiation dose at 600 volt for 150 micrometer active thickness, and 400 volt for the 100 micrometer active thickness. Also, there is some investigation for different designs of, for example, the bioinstance structure with solution like pack-through, bias rail, and temporary metal, and also some investigation on how to optimize the end implant. You can see here on the left plot some example where we see that, for example, if we want some this solution of the bias rail, we lose something when we are very low voltage. But here the message, you see here the line at 97%, that the efficiency when we have enough bias voltage, for example, here 400 volts at the level of irradiation that we are looking at, all the solution will give us the required efficiency and performance. So there is now for planar sensor a market survey ongoing, and the results on this market survey are foreseen for the end of the year. And then we'll start with pre-production. For 3D sensor in the innermost layer, also here we are moving from a double-side technology that was used in IBL with larger pixel cells to a single-side technology where we use this support wafer in which the columns from the same side inside the bulk. And we have this smaller pixel cell, which in 3D also means more radiation hardness. So the active thickness is also reduced from 230 to 150 active layer of silicon, which is necessary to reduce the cluster size and the data rate. Small pixel cell means high occupancy, resolution, and there will be two solutions, two pixel cell in the innermost layers, 50 by 50 in the rings, and 25 by 100 in the flat barrel part. This solution of 3D has been chosen because of the superior radiation hardness, which has been measured at 1 times 10 to the 16 with an heat efficiency of more than 97%, are very low operation bias voltage of 80 and 140, between 80 and 140 volts, depending on the features. And also very important is the low power dissipation of this kind of sensor, which can operate at very low bias voltage. And so they can keep the power dissipation to less than 10 milliwatts per square centimeter at the benchmark measurements of -25 degrees. So here you can see some measurements of the efficiency, and the news is that the pre-production already started. We passed, there was like also in this case a market survey that was passed.
Sorry, Stefano, 1 minute left. Yeah,
I'm almost there. So talking about data transmission. So we have here our quad modules from which the readout is done on 4 links at 1.28 gigabit per second. And then from PP0 out of the flex, there is like a transmission through twin-ax cables over 6 meters cables. and then the gigabit receiver and these opto boards, which transform the signal from to optical signal and ship out at 5.12 gigabits per second out then to our readout system. So there is already test system development from this, which most of the parts already in place and tested. Other demonstrator program have been are already ongoing or completed, that evaluates the thermal mechanical studies and performance of the pixel detectors. So, for example, here there are some simulation where you can see the difference of temperature inside a quad modules, and these simulation results are within the thermal specification. Also, some prototypes of the end cap systems done with the FEA4 based, so the previous chip prototypes. Also with for the staves and for the rings with already some serial powering chain. And in the, also for the outer barrier, there's a demonstrator program for thermal and electrical properties with full-size prototype types with 7 quads and 13 duals, and also in this case testing the serial powering chain. There is a poster about that, so I invite you for more information to refer to that. So this is my summary. So we are preparing the new pixel detector to face the challenges of the high luminosity LHC, which are radiation hardness, low material, and increased granularity. We will have these 5 pixel barrel layers and rings with a new radiation hard readout chip, which is ready, planar sensor in the outer layers, and 3D sensor in the innermost layers, and very important, the serial powering chain and the CO2 cooling. There are several market surveys and final tests and developments ongoing, and we are moving now from basically the design to the prototyping, and we are getting ready most of the system for the pre-production. So thank you.
Thank you very much, Stefano. Very nice talk. Are there questions? Paula.
Oh, hi, this is Paula Collins from CERN. Thanks for the nice talk, Stefano. Just a quick question. Katja mentioned in the previous talk that they could consider replacing the innermost 3D layer. Is that something that you also consider?
Yes, I mentioned before. Actually, the first 2 layers, so both the 3D one and the first planar layer, so layer 0 and layer 1, are foreseen to be replaced at half of the dose.
Okay, thanks.
Yeah, I had a similar question. So it's you plan to replace them once?
Well, the possibilities, of course, they are done in a way that could be replaced even more than once. At the moment, the baseline is to have 1 replacement.
Thanks. Is there any other question? I don't see anything. Thank you very much, Stefano. Then we can move on to the next talk, which is Dennis Sperlich from University of Freiburg, talking about the strip part of the ATLAS ITK upgrade.
Yes, welcome. Yes, this is about the strip part for the phase 2 LHC upgrade. And so far, as most of you, I guess, know, LHC delivered about 170 inverse femtobarn, ATLAS, or slightly more at ATLAS, we call it 170. And there will be another data taking period, which increases this number to around 300 inverse femtobarn. And to go on even further than there needs to be a significant upgrade of LHC and all the detectors to reach a goal of about 4 inverse autobahn within the next 10 years. Oh, 10 years of then data taking, so it's another 13, 15 years. And the challenge is that the track density is huge. On the right, you see a simulated TT bar event with a pileup of 200, which is about what we would expect in these circumstances. And also the radiation damage, as you've seen in the previous talks, gives significant trouble for the designs of the new detectors. And so the plan is that we replace the complete inner detector and upgrade calorimeters and muon systems, like the new small wheel upgrade, which is currently happening, is already part of this full program. The schedule for ITK is that it will be installed by next shutdown, but we need to start building essentially now. The designs are mostly done, and we are about to start pre-production. There are still some final design checks ongoing, but the first pre-production parts are already incoming, like sensors. We already get pre-production sensors in. COVID-19 now delayed a little bit things, so it's essentially pushed back the start of module pre-production a little bit. Well, depending how long COVID goes, it might be slightly longer than a little bit. The envelope, as we've also seen just in the pixel talk, is that we take out the full inner detector. So the current inner detector has pixel, SCT, and TRT, and goes with tracking up to ETA 2.5. And we replace everything. The inner part stays pixel grows a little bit, and then the part which was occupied by SCT and TRT is now fully stripped, spiral, and end cap. And there's also quite likely a high-granularity timing detector at the most outer edge of the cylinder. The tracking will be up to ETA 4, but this is mostly a pixel matter. Strips, due to geometrical constraints, only go to essentially ETA 2.5 still. The performance requirements for the strip part is that we need to achieve the same physics performance in a much harsher environment. So the track density goes up significantly. So we need finer segmentation to keep the occupancy in the 1% level. But we should not increase the material budget. And as you see from the old expected signal material budget, we are still slightly lower in the current expectation. And the real one is actually higher than the expected one. Yeah, we aim to be better in terms of material for the calorimeter, and also the higher radii for silicon means we have way more silicon area, both in pixel and strips. To get the occupancy down, the strips need to be shortened. SCT had 6 to 12 centimeters, ITK will have 2 to 5 centimeter long strips. Module data rate is increased quite a bit from SCT modules, which were read out with about 40 megabit per second, and ITK strip modules have up to 4 times 640 megabit electrical links coming out of them. And the radiation tolerance is essentially a factor of 5 between SCT and ITK modules. The module itself is the, I think, most complex part of the ITK strip system. It's based around the sensor, but on the sensor then sits the flex PCB, which ties everything together. There are passive compilers soldered on the flex PCB, but then ASICs are already glued on and wire bonded to this flex. This flex is glued to the sensor, and the front end bonded from the front end ASICs towards the sensor. There's also a DC-DC converter, which converts 11 volts to 1.5 volts, also glued on the sensor. And there will be about 15,000 modules installed in the final detector. These modules then go onto staves in the barrel and petals in the end caps. There are 14 modules, same modules on each stave side. The petals have 6 different module types due to geometry. So the petal in the end spans the full ring. The barrel does cylinders on the outside, essentially. And modules on both sides, and there's space, and to give space points, there's a stereo angle between 40 and 52 milliwatt between the two sensor sides. The data is then also converted into optical to get it out of the detector. So the 640 megabit, 14 640 megabit signals go into 10 gigabit links, and there are up to 4 fibers of data coming out of each petal or stave. The sensors are 320 micron thick silicon, NNP doped, like CMS now. There are 8 different sensor designs, 2 in the barrel, 6 in the end cap for geometric reasons, and the 2 barrel ones are inner and outer. So shorter and longer strips. They are made on 150 millimeter wafers and are biased between 100 and 500 volts depending on radiation damage. And the required radiation tolerance is about 1.2 times 10 to the 15 Newton equivalent per square centimeter and 50 megawatt. There are also mini sensors and other test structures on these wafers. That's why they look a little bit cluttered, but yeah, they are all designed already, and we have essentially all of them in hand as well. Each strip is also tested by HBK vendor, and a subset is also then verified with reception tests in institutes. So we have a quality control chain there in place. The data and control is handled on the hybrids and power boards. The hybrids, as I said, are sitting on the sensor itself and house the front-end ASIC, the ABC star, ATLAS binary chip, with point-to-point data links to the hybrid control chip, which aggregates it into 640 megabit. Also, this hybrid control chip creates a common bus of clock control and readout requests, which is then passed to all the ABCs to control, clock and control. There's a pipeline for level 0 and a FIFO for level 1 trigger events on each ABC. So we support on front end essentially level 0, level 1 trigger scheme. We also have support for regional readout requests if ATLAS decides to utilize them. There are 13 different NCAP hybrid designs and 2 barrel hybrid designs purely for geometric reasons. The power board, as I said, goes from 11 to 1.5 volts for the all the ASICs. It also houses another ASIC, the Autonomous Monitor and Control ASIC, which measures temperatures, voltages, currents, controls low voltage and power states of the hybrid. It also can switch high voltage on a module, which means we can supply 8 high voltage lines into a stave of 28 modules. And if one module goes in high voltage short, we can switch this single module off and don't lose more. There are 4 different designs in the NCAP and 1 in the barrel, again, for geometric reasons. The assembly is done on the module level by placing the hybrids with tools on the sensor. These tools or custom tools are machined aluminum and everything is handled with vacuum. The hybrids and ASICs are held down and lifted with vacuum. And we need to achieve about 50 micron placement precision, but this is purely to not collide with anything and to allow easy wire bonding of everything. The loading is then done on the pedal stave carbon fiber structure. So all these modules go on these bigger structures. And in the barrel case, the alignment is done with also again custom tooling, which works quite great. In the end caps, this would be slightly too difficult to have this weird wedge-shaped custom tooling which holds 2 sensors next to each other and everything. So we opted to go for 4-axis CNC gantries to move and place the modules in the end caps. This is slightly more versatile. For both, we need 40 microns accuracy, but we aim for and can actually reach 20 microns. The testing is a very crucial part of the whole production process. We make sure that everything is tested, measured several times before it goes into the detector. So the hybrids and power boards are 100 hours even before they are glued on a sensor, because the sensor is reasonably expensive compared to hybrid and power boards. So we make sure that they work before they go on the sensor. Also, power boards are thermally cycled before they go on a sensor, on a sensor. And then when we have these modules completed, they are thermally cycled 10 times between -40 and +40, which is the full operational range the detector is allowed to see. When this happens even before they go on a pedal or stave, so they form more expensive and bigger structures. After each shipment of things, so all these things might be shipped or might not, depending on where exactly in the world stuff is assembled, everything is retested except for stuff like thermal cycling. This is only done once per part. Pedals and stave are then tested cold again at assembly and integration site to make sure that before stuff is then put into even bigger structures, before it goes into the pit, it actually works. In addition, destructive tests are done on some parts, and design validation is done like with test beams and other bigger system tests. We are currently starting to build bigger structures as we get parts in hand, essentially. And everything is tracked in a database. To conclude, the ITK strip will replace the SCT and TRT for the High-Lumi LHC upgrade. The physics performance will be maintained, even though the environment is much harsher. The design of nearly all components is done. We passed, I think, all the design reviews by now. And only a small number of tests are pending before module production can start. So, for example, we found an interesting noise source recently when testing bigger structures. The production strategy and infrastructure is mostly in place, but sadly COVID-19 now had some impact on the schedule, which at the moment is actually still on target, but we are getting close now to critical paths for high Lumi LHC upgrades. I would assume that most experiments are in a similar situation. So, yeah.
Great. Thank you, Dennis, for the very nice talk. Other questions? Katja.
Hi, Dennis. I'm impressed by your statement that you run the hybrids for 100 hours before using them on the sensors, because you also have at least 30,000 hybrids or maybe more.
Yes.
So we are trying
test structures like here in the top picture.
So how many hybrids can you fit in such a crate, and at how many places do you do that?
In all places which build hybrids, which is most of the sites, and one crate can hold in the barrel case up to 36 hybrids.
Okay, but you have to run it for 4 days then.
Yes, which is easily I think the barrel sites might have two of these crates per site which build hybrids. In the NCAP, they fit slightly less in, but we produce like 2 to 3 modules a day, which is up to 6 hybrids a day. And then if there are 6 slots for 6, it works out with 1 crate per module building site, essentially.
Okay.
It's reasonably cheap. It's 1 Genesis and a custom backplane and some few parts.
Yeah, okay. Yeah, impressive, because we are trying to reduce the time that a hybrid test needs to a few minutes, basically. So, okay, I have to think about this.
A few minutes are fine. I also don't know whether we will find something. It's just a thing we can do reasonably for reasonable cost, because it's only running at slightly elevated temperatures. It's not. This is not thermal cycle. Thermal cycle is only modules, which is way more of a headache actually than the hybrid.
Thank you.
Should unmute. Are there other questions? If not, I have one. You said something about regional readout could be enabled.
Yes.
Can you say a little bit more about that?
Well, we have the full support in the in all the ASICs. So it's essentially implemented by having 2 priorities for readout requests. So if a level 1 trigger comes in, then we issue a normal low priority trigger readout to the ABC. And if a regional readout request would come in, then there's a second 5.0 for triggers which are worked on for high priority readout, and then this would then precede essentially the next readout, which is possible.
That would get linked on level 1 then with the other information? Yes. Okay, interesting.
So yeah, it's just supported. It's fully simulated, and we so far tested. So everything we tested so far showed that it should work. Good.
Thanks. Are there any more questions? If not, let's thank Dennis, and we can move to the next speaker, which is Timothy Evans, talking about the LHCb VELO upgrade.
Hi, I'll just okay, so you can see me. And okay, I'll share the screen. Okay, so can the slides be seen by everyone, or?
Yes, but not yet full screen. Now it's good. Thanks.
Okay, great. Okay, so I'd like to tell you a little bit something about the LHCb VELO program for second series upgrades for running in the high luminosity era. So I'll first talk a little bit about the LHCb schedule, because I think it's a little different to the ATLAS and CMS ones. So our original detector ran from 2010 till 2018, at which point we shut down. We're in this current shutdown LS2, and we undergo a major upgrade to be able to record luminosity at a much higher rate. We'll run with this iteration of the experiment until about 2030, and then we'll shut down again, undergo a second series of upgrades, and then LHCb will be able to exploit the full high luminosity LHC luminosity. So For us, this is about a factor of 7.5 times what we get in upgrade 1. This means we get about this much more data. This also means we get 7.5 times the radiation damage and track densities and everything like this. So rather significant improvements are needed to the detector to maintain or hopefully improve the physics performance, but also in order to be able to survive the rate and the radiation dosage. There's a huge amount of physics you can do with all this data, though. So you can find this documented very nicely in the expression of interest, the physics case, which are linked below. If you want more information about the VELO, in particular the upgrade 1, there's a very nice talk by Peter this evening that you should all go listen to. And you can find the link here. Okay, so what are the conditions that this detector is actually going to have to deal with? So we're going to have to deal with a pileup of about 50 proton-proton collisions in every bunch crossing, which is comparable to what ATLAS CMS are expecting significantly sooner, but I'll hopefully convince you in a few slides that this is actually much more challenging in the forward region than in the transverse directional. So the first question to ask is can we actually read out and reconstruct the detector with this much pileup? The second really challenging requirement is that the integrated fluence at the innermost point of this detector is a little bit insane. So if you were to leave the detector in where it is for the entire lifetime of the high lumi, it would be integrated fluence of about 6 times 10 to the 16 neutron equivalent dose. So this is extremely tough, and I'll show you towards the end of the talk a little bit about some of the strategies we have to try and deal with this. So, and also the readout rate from the chips is huge. So with all of this rate, I mean, basically the hybrid pixels are the only game in town to be able to deal with this. So relatively small pitch of 50 microns or less with sensor and ASIC fabricated separately and unbonded. But so other than that, what kind of detector do we have to build to be able to deal with this? So the first question we sort of ask ourselves is can we actually reconstruct the physics that we want with a detector that looks similar to the one we have now? So if we start off at the top of this plot, you see that the distance between the primary vertices in upgrade 1 is a little over 4 millimeters on average, the next vertex. And at this point, given the resolution we have on the tracks, which is what's plotted here, you see that actually we can resolve this very, very nicely because basically all of the tracks that we record in the VELO, the resolution we have in them is much better than the distance between the vertices. So reconstruction is straightforward. Now, if we go up to 50 interactions per bunch crossing, so there's this lower line, so about 1.5 millimeters, you see that this is going to be really tough because our resolution is comparable to the distance between the vertices. And here you can kind of see why there's a difference between LHCb and ATLAS and CMS, that we're really interested in this forward region, where just geometrically it's more difficult to separate the vertices along the z-axis. This is where all our physics is the region where this is not so straightforward to do. Now, this is a nice picture of this. How does it look in practice? So we simulate the detector with the upgrade 2 conditions, and we find out, as you might expect from this plot, that we're going to lose more or less half the primary vertices due to basically merging them together into blobs of these things, unless we change something in the detector. So another way of looking at this is just a sort of toy Monte Carlo simulation of some vertices, and you see that every bunch crossing is a real mess in the upgrade 2 conditions for us. But maybe there's some tricks you can play. So the proton bunches in the LHC actually overlap for a finite time. The proton-proton collisions are not all synchronous. So the RMS of this is about 180 picoseconds. So if you can resolve them in time for bunch crossing as well as in space, maybe you can still reconstruct stuff. So if we just take a time slice of 30 picoseconds here, this already looks much better, and hopefully everyone can make out by a few interactions. But yeah, I mean, this will need a really, really excellent time resolution though in order to pull this off. So tens of picoseconds on every hit. in order to be able to do this. And then we say, does this work? And we say, and we simulate this as well, and we see it does work in the simulation. If we add a 50 picosecond timestamp per hit, just our initial study showed we can almost completely recover the vertex reconstruction performance that we have in the upgrade detector. So this is a very, very promising way of meeting this particular part of the challenge. One of the good things about having a per hit time measurement rather than just measuring it for every track is that you can then also use the time measurements in the track reconstruction itself. So four-dimensional tracking is the really good thing about this is it's uncorrelated to the spatial quantities of the track. So this, by using this information, you get a much better uniformity of the tracking efficiency. Why is this important? Because where tracks come from is completely correlated with things like the K times that are actually very related to quantities that we want to measure. So any non-uniformity in tracking efficiencies here is going to be a problem from the point of view of systematic uncertainties and things like this. So 4D tracking is really quite good for improving this. And also it gives us really serious reductions in the ghost rates as well. So we can track with less than with about 1% ghosts in high lumi conditions by using 4D tracking. And again, just to emphasize, these are just the first studies of what we can do with this sort of technology. We expect further improvements as we become more sophisticated and we exploit hardware like GPUs and FPGAs to really get the most out of this information. So hopefully I can see that timing is absolutely mandatory for dealing with the high luminosity conditions in LHC. So a natural question is, could we also consider something more like ATLAS CMS, which is a timing plane-like measurement, where you just have single, more precise timestamps of, say, 30 picoseconds. Now, there's a few quite serious downsides to this in our case. One of the most serious is it's not really possible to cover the full VELO acceptance with timing measurements if you do this, just because the timing plane becomes enormous. You could maybe cover the LHCb acceptance, but the VELO acceptance is quite a bit bigger, as if you see in the previous plots. And you would lose the timestamps on these tracks that are incredibly important for the vertex reconstruction. You wouldn't have any benefits to the track reconstruction, and actually, because we're interested in a much softer momentum spectrum, time of flight differences are actually quite a problem. If you put this thing 1 meter from the interaction, it's much better to make the measurements very close up. You would plausibly have to do something like doing the particle identification before you do the vertexing if you put the measurement a meter away, which would be a nightmare for the trigger. You potentially have problems with occupancies if you have the large pixels still, and again in the inner region, and you have to develop 2 ASICs at the same time, which is difficult. So clearly we want to build a full 4-dimensional tracker, and the question is just how do we do it? So the first step along this is the readout ASIC, which we have some advantage here, and the VELOPIX ASIC that we're using for the current upgrade has been developed in collaboration with the Metapix group, who already have this very impressive fast timing readout chip with a 200 picosecond TDC, so Timepix 4, and we can see that this is clearly going to be the stepping stone for us to move to the next generation of chip technology, which I've just tentatively labeled PicoPix here, where we will need to go have a much better time resolution on the length of the project we're talking about. This is possible, and also to emphasize the other requirements in the chip are also extremely demanding from the point of view of the amount of data you have to push off this thing. So there's a lot of R&D to do, but we think it can be done. And just to emphasize on this first step, and this is the Timepix 4, and this has arrived and it can read out data. So here we have a nice picture of the source. I should say this chip is enormous. You have 4 sensors bonded onto it, whereas it's almost the other way around for the VELOPIX. Okay, so as well as a fast ASIC, ironic thinking about fast things, but as well as a fast ASIC, you also need very fast sensors. So maybe thin planar is good enough, but maybe it won't be. So two possibilities are the LGADs, which have really good time resolution, but they have very low fill factors for small pixels, and they're probably not radiation hard enough. But there's R&D ongoing to see if you can make it better. Also, 3D sensors are very promising. So there's a very nice time-optimized 3D sensors from the TimeSpot collaboration, which get down to about 15 picoseconds. But they also have inactive areas, so one has to design the detector with this in mind. CERN is very interested in generically in the fast timing detector R&D for FCC, BDF, etc. So it's one of the work packages in the R&D program generically. You can find 2 examples here of activities that are ongoing with sources and simulations. Okay, so the other massive challenge is the radiation damage. We said before it is about 10 to 16 neutron equivalent, which is basically the point where thin planar sensors become useless. So are you going to have to replace this regularly, or can you do something else? And that something else might be that you can move the detector further away. But then you ask, well, why have you put it so close in the first place if you need to move it out? And the reason is that it's very important for the impact parameter and secondary vertex resolutions to have the first measurement as close as possible. So you then have to change the rest of the detector as well. And basically this means smaller pixels and removing all of the material. So maybe it's possible, but it's certainly not it's certainly not a panacea. Okay, so the other solution, as I say, is to replace the detectors regularly, which has to be designed at the beginning. So there's plans, for example, that you could have the detectors on cassettes that you can spot very quickly. And also for either option, you really want to remove the RF foil as much as possible. So there's lots of studies ongoing to see how thin this thing can really be made, and maybe you can support it on the models themselves. Okay, the last thing I'm going to talk about is just the cooling, which just flash up for a second, which is we planned, so the current upgrade is using a biphase CO2 cooling on microchannel plates, and these are very good for lots of reasons, but they're also very expensive. So it kind of goes against having the thing being replaceable. So maybe you can mitigate this by having them small microchannel plates, or maybe you go to a different technology, for example, having a 3D printed titanium, which is much cheaper and more flexible if you want to put things in at angles, for example, for 3D sensors. And we already have prototypes of this actually, because it was considered for upgrade once. So this isn't just sci-fi technology. Okay, I won't go through the conclusion slide because I'm running over quite a bit. But thank you for listening.
Thank you very much for this interesting talk. Are there any questions? We have time for one, maybe. No, I don't see any. So in the picture where you had the Medipix chip with the 4 sensors, which sensors were those?
I'm not sure, I'm sorry.
Okay. But so how big is this thing in the end?
So this thing is it's 7 centimeters squared. So I mean, it's roughly the size of 4 of our it's roughly the size of 4 time pic 3s. It's a little smaller. So it's 512 by 448 pixels.
Okay. Thanks. Are there any more questions? Doesn't look like it. Thank you again. And we can move to the next talk, which is Andrea Rossi from INF and Padova, about the ATLAS upgrade for Run 4 and beyond.
Hello, can you hear me?
Yes, hi.
Okay. So, good afternoon, or good morning, good evening. It's a pleasure for me to present ATLAS upgrade plans for LHC Run 4 and beyond. So this is how ATLAS is gonna look like in a few months, some months from now. And this picture differs from the one you might be used to because of a major upgrade ongoing. In particular, we are changing the readout of the time projection chamber. We are inserting a fast interaction trigger. We are inserting a Muon forward tracker in front of the Muon absorber, and we are installing a new inner tracking system that we will call Inner Tracking System 2, so ITS2. So this upgrade will be we'll discuss in the detailed talks that you see here. So let's see what we plan to do next for Run 4, so during LS3 in 2025. So we plan a further upgrade of the inner tracking system, replacing the 3 innermost layers with a novel silicon detector. And we want to instrument the forward region with a calorimeter, focal. And let me start describing this last piece that we want to add. So the focal will consist of an electromagnetic and hadronic calorimeter. The electromagnetic one will be a high granularity silicon tungsten sampling calorimeter for measurement of the red, gamma, and pi zero, and will consist of layers of low granularity silicon pad sensor and a couple of high granularity silicon pixel layers that are fundamental to get a detailed view of the shower profile with a high resolution for two shower separation that is fundamental to separate, to disentangle between the red gamma and gamma from pi zero decay. So here you can see some nice picture from test bin showing how well this pixel layers allows to get a detailed view of the shower profile. Now, the goal of the focal is to constrain gluon nuclear PDFs as small Bjork and X, where indeed even for proton below x equal 10 to the minus 4, there is limited information. And the idea is to do this by measuring isolated gamma and forward rapidity that allow to probe to be sensitive to the gluon PDF already with processes at leading order, as you see from the diagram here, differently from what is possible with a yes experiment when one has sensitivity to gluon PDF only via next to leading order processes. So in the right figure, what you can see is the X coverage at various facilities with different experiments, and you can appreciate that focal allows to get to the lowest ever X values, even lower than LHCb thanks to the ETA coverage. So while this low X region is important, from the IS experiment like those at HERA, we know that the gluon PDF increases at low X, and indeed from Digilap and BFKL evolution equation, one would expect an infinite growth. However, these equations are linear and include only splitting terms. When the gluon density starts to become large, even non-linear terms might be important, like the gluon fusion one, and that may ultimate tame the gluon PDF. So testing these gluon fusion processes and the possible saturation scenario is of course interesting per se, but also simply the fact that we have a limited information on nuclear PDF at low X introduces very large uncertainty on theoretical predictions that make it difficult to disentangle QGP-induced effects from cold nuclear matter effects. So what you see here in this figure is the performance that we expect to achieve for the nuclear modification factor for isolated gamma in proto-lead collisions. So this factor is the ratio of the yield of a given particle, like gamma in this case, in the nuclear collision system, P-lead in this case, with respect to what we expect from proton-proton collision. So looking at the blue band, you can see that we can achieve an uncertainty smaller than 20% from 6 GeV on, and this uncertainty is much smaller than the theoretical uncertainty from nuclear PDFs that you can see from the continuous black line here, one theory, and another theory is represented by the gray band. So from these data, we can set constraints to nuclear PDFs, and this you can appreciate better in this figure where the ratio of the nuclear to proton gluon PDF is shown. The gray band represents state-of-the-art next to the leading order PDF fit to the IS data. And you can see that basically below 10 to the minus 2, there is no constraint. And if these fits are repeated, including the focal data, I mean, something like similar to what you showed in the previous slide, you can see that we can set significant constraints, looking at the red bands, between 10 to the minus 2 and 10 to the minus 5, with a precision that exceeds what can be obtained with experiments at the electron-ion collider here reported in green. So coming now to the other detector that you want to upgrade during LS4. So as I said, we want to replace the first 3 layers of the ITS2 with a novel vertex detector consisting of a wafer scale, ultra-thin monolithic active pixel sensor in curved, perfect half-cylindrical layers. We plan to move most of the electronics at the edge of the sensor, and given the very low power consumption, we can use airflow cooling. And thanks to this, we can bid down the material budget down to unprecedented values, as you see here from the table. We will build also a new beam pipe with a smaller radius that will allow us to place the innermost layer very close to the beam line, 18 millimeters far from it. And this, along with the reduction of the pixel size, will allow us to improve by a factor 2 the resolution on the track position at the primary vertex, as you see here from the figure, over a wide PT range. Also, we will be able to improve significantly the tracking efficiency for PT smaller than 200 MeV. And well, with the ITS3, we think that most of the analysis we plan to do in round 4 will be boosted. Here you have an example for the electrons that you want to use to study the electromagnetic radiation from the core gluon plasma. So the left plot shows the invariant mass differential spectrum for the electron pairs after the subtraction of the background from conversion. And in the middle figure, you can see what happens after we subtract also the contribution from charm. Then we can fit this the invariant mass distribution between approximately 1 and 2 GeV to extract what is an effective temperature of the core gluon plasma medium. And the uncertainties on this temperature obtained from the fit is reported for ITS2 and ITS3 in the rightmost figure. And you can see that thanks to the reduced material budget that of course reduces the conversion contribution and to the improvement in the charm rejection, we can reduce the statistical and systematic uncertainty on this temperature significantly. Now, another physics topic for which we expect a boost in the performance is the study of the heavy core hadronization. In particular, with ITS3, we can really improve the precision in the beauty sector. And what we want to probe is whether a beauty core can recombine with the surrounding cores from the medium, so with the mechanism coalescence that differs from the usual fragmentation in vacuum. So this mechanism is expected to enhance the production of baryon state with respect to meson 1, and therefore it's important to measure the lambda B baryon. And here in the left figure, you can see that with the ITS3, we can improve the statistical significance by about a factor 2.5 over the whole momentum range studied. And another effect from coalescence is the enhancement of B sub S due to the fact that strange cores are produced more abundantly in the QGP. In the middle plot, you can see that with the ITS3, we can improve the statistical significance by about a factor 2 for B sub S, and also extend the measurement down to 2 GeV, which is the most sensitive region for coalescence, as you can see from the right plot, where the performance on the RAA for B sub S is shown, and you see that the low PT region is the one in which the theoretical expectation for B sub S and non-strange B differ the most. Now, another fascinating idea we have in mind is the search of charm nuclei, in particular of C-deuteron, which is as a deuteron but with the lambda C replacing the proton. So this state was predicted to exist already in the 70s, but was never observed. Its production is expected to be enhanced in lead-lead collisions with respect to proton-proton, but still, if it exists, the signal we expect is very small, and it will be very challenging to reconstruct the decay that should produce also a deuteron among the decay products. So one of the key features would be to exploiting the C-tau, which is short but non-negligible, around 60 micron, to exploit the deuteron displacement from the primary vertex. However, for this, we need a very good resolution, especially for a massive particle as the deuteron. And in this respect, the ITS3, which has a very low material budget, helps a lot. And here in the figure, you can see that with the ITS3 shown in the right panel, we can separate signal deuteron from background 1 better than with the ITS2. Now, coming to last topic, so what we plan to do in round 5. So the ambition to design a new experiment to continue with a rich heavy ion program at the high luminosity LHC was mentioned recently in the update of European Strategy for Particle Physics. The goal would be to study proton-proton, proton-nucleus, and nucleus-nucleus collisions, not necessarily lead-lead collisions, at luminosity higher up to factor 50 than what we can get with LHC in round 3 and 4. Last year, our first document outlining the possible detector concept and physical opportunities was submitted to arXiv. So this is still just a concept, and the idea would be that of a compact, only all silicon, nearly massless detector, providing excellent low-PT tracking capabilities. We may achieve this with truly cylindrical layers with curved wafer scale ultra-thin maps, so using the same technology that we plan to use for ITS3, with the addition of end caps to extend the ETA coverage up to 4. And we are considering the possibility to place to locate the innermost layers inside the beam pipe, and we want to instrument the outer layers with time of flight measurement for particle identification. With this design, we could get access to doubly and triply heavy quark hadrons, perform precise measurements of the electrons and of soft and ultra soft photons. And this can give us an unprecedented insight into the QGP world, especially for topics like heavy quark coalescence, chiral symmetry restoration, and also we can do precise measurement of the medium temperature. So this brings me to my summary that I don't need to read. Instead, I want to leave you with this nice picture of a fully functional Alpide sensor curved. So this is what we will plan to use for ITS3. And this shows that this project is well on track. So that's all. Thank you.
Thank you very much, Andrea. Other questions about the ATLAS upgrade? Can you say a little bit more about where the prototyping for the maps is standing at this point? Also with respect to radiation hardness, for example.
Well, no, I don't. I mean, we have several prototypes, and but you mean for ITS2 or ITS3? 3, I guess. Yeah. We have done some prototypes, but I don't know. I cannot give you more details. Okay. Are there any other questions? If not, thank you, Andrea. We can move on to the next speaker, which is Andrew Hart from Rutgers University, talking about the level 1 track trigger and CMS. Thank you.
Thank you. Let me share my slides. Okay, they should go full screen, and there they go. So the high luminosity LHC, as I'm sure we all know by now, is expected to achieve unprecedented luminosities for Hadron Collider 7.5 E34. And the enormous amount of data that this will provide to the experiments gives us great opportunities for physics, but it's also very challenging at every stage, from data collection and triggering to analysis. And so the question is, how do we ensure that we get the most out of this data? And a key component of the strategy for CMS is to introduce tracking in the level 1 or L1 trigger. And so here I'll give an overview of the system currently being developed, as well as the latest results from it. So we have many exciting possibilities with a 4,000 inverse femtobarn data set, as we expect from the HL-LHC. For example, precision measurements of the Higgs boson, including potentially self-coupling measurements via di-Higgs production, extended discovery reach for BSM physics, or more optimistically, precision measurements of BSM physics that we discover between now and the HL-LHC. And also observing very rare standard model processes that could be sensitive to BSM physics indirectly. But of course, the cost of these physics possibilities is enormous amounts of pileup that we have yet to have seen in our data. So in the upper plot, you see the distribution of pileup that we saw in 2018. And for the HL-LHC, we expect up to 200 overlapping collisions per bunch crossing, which is way off the scale of that plot. So the trigger system has to reduce the 40 megahertz input rate to about 7.5 kilohertz in the presence of this enormous amount of pileup. And tracking at level 1 is central to accomplishing this. We think that without tracking, the L1 outputs could be as high as 4,000 kilohertz with 200 pileup instead of the 750 kilohertz that we need. So this is a schematic showing kind of the layout for the entire L1 trigger system for the HL-LHC. And you see in the upper right is the track trigger, which will be new for the HL-LHC. So we have the track finder, which actually is the part that assembles the tracks and fits them. And then these are fed into a global track trigger, which reconstructs track-only objects, including vertices and, for example, track met. And then these also go into the global muon trigger and a correlator trigger, which receives input from the calorimeters, which matches tracks with muons and with calorimeter deposits. So then the global trigger receives, it can receive a list of something like particle flow candidates, similar to how to what we use in offline analysis. And so the way that we use this this new feature of the level 1 trigger, so usually in order to reduce trigger rates, we increase momentum and energy thresholds, but this can quite obviously hurt physics potential for lower energy physics that we might want to target. And it's also insufficient by itself when we talk about HL-LHC rates. So in the plots, you see the trigger rate versus muon trigger PT threshold up top, and versus ET threshold for an E gamma trigger on the bottom. And you see that as we go to higher and higher thresholds, the rate levels off. So you actually gain less in terms of reducing the rate the higher you increase the thresholds. So it becomes less and less effective. And so L1 tracking provides a powerful alternative to this traditional strategy. And you can also see that in the plots. So for both the muon trigger and the E gamma trigger, when we include tracks at level 1, that has a profound effect on the rate in terms of reducing it, especially for muon and electron triggers. And this comes from improved muon PT resolution and identification, better electron identification, as well as photon and tau identification, and also from the ability to associate tracks with vertices and to distinguish them from particles coming from pileup. And so we've seen this diagram of the HL-LHC tracker before. So I'll just say the upgraded inner pixels will not be used for the L1 tracking, but the outer tracker will be. And so it will be composed of 6 layers in the barrel and 5 discs in the end caps. And the outer tracker will be composed of PT modules, as has also been shown in previous talk in this session. So these enable front-end PT discrimination, which is important for reducing the data volume by about an order of magnitude right at the front end. And so then stubs are formed from correlated pairs of clusters that are consistent with at least 2 GV track. And then these actually form the inputs to the L1 tracking algorithm that we're developing. And so these stubs are formed by PS modules, which combine a pixel and a strip sensor closer to the interaction point, and then strip or 2S modules further away. So then once the stubs are formed at the front end, they then go to data trigger and control, or DTC boards, that perform stub pre-processing and distribute stubs to the track finding processor boards, which actually run the tracking algorithm for L1, and which receive a new event every 450 nanoseconds. And this system is parallelized both in time and space. So it's time multiplexed with a factor of 18. And also the detector is divided into 9 phi sectors, or nonents, with stubs being shared between sectors, but tracks are not shared. So you see the shape of a processor nonint highlighted in green in the center of the slide. And that shape is such that a track with at least 2 GeV of PT will only fall into one nonint and not a neighboring one as well. So we don't have to share, we don't have to remove duplicate tracks between sectors at the end of the algorithm. But the darker green regions are regions where stubs have to be shared between neighboring sectors. So we sort of front load the sharing between sectors. So then tracks are seeded by stub pairs in certain layer disk combinations, and you see those illustrated at the top there. So there are 3 barrel-only seed combinations, 2 disk-only seed combinations, and then there are 3 seed combinations that fill in the in-between region. And in order to reduce combinatorics, only stub pairs that are consistent with PT greater than 2 GeV are kept. And this is accomplished by coarsely segmenting the tracker layers into virtual modules, and then only those virtual module pairs that are consistent with the PT threshold are even connected in the firmware in order to reduce the combinatorics that have to be considered. Then from these seeds, we calculate helix parameters and projections to other layers and disks. And this assumes that the tracks originate from the beamline. And these projections are then used to calculate residuals with stubs in those additional layers and disks. And if the residuals are small enough, then those stubs are matched to the track. And this yields the full tracks that are then the inputs to the final track fit. But before the track fit can take place, we have to remove duplicate tracks, which naturally arise in this algorithm. Most of them come from redundancies that are built into the seeds. So for example, a central charge particle will usually be seeded 3 times by the 3 barrel-only seed combinations. And we also have some duplicates that come from nearby stubs in a given layer that yield very similar tracks. And that's illustrated in the cartoons on the slide, where you have 2 stubs that are very close to each other in the second layer, and that results in 2 nearly identical tracks. So these duplicates are removed before track fitting by merging any tracks that share at least 3 stubs. So then after duplicate removal, we can finally fit the tracks. This is done with—
2-minute warning.
Thank you. This is done with a Kalman filter, which is roughly similar to what's done offline. So I won't go into too much detail here, but there is a beamline constraint by default. So 4 track parameters are fit, but we do have the possibility of also fitting the transverse impact parameter. So here you see the L1 tracking performance. So we expect about 40 reconstructed tracks per sector per event, which is very reasonable and manageable. And we also see great efficiency across the entire tracker, at least about 95%. And also we see good longitudinal impact parameter resolutions down to about 1 millimeter for the central region, which will be critical for vertex association. Now, this is all a baseline algorithm. We're also exploring various extensions. One of the most exciting ones is the possibility of adding displaced tracks at level 1. And this is under active development. So this is achieved with 2 additions or modifications. So first we add 3 triplet seeds. So we need triplet seeds so that we can remove the beamline constraint when projecting 2 additional layers. And those are illustrated in the plot there. So there are 3 barrel-only ones and then 2 in the overlap and forward region. And then, like I just mentioned, for the fit, we have a 5-parameter Kalman filter fit that includes the transverse impact parameter. And so the initial results for the displaced tracking are promising. So in the bottom left plot, you see that we achieve good efficiency up to about 5 centimeters in impact parameter. And we expect the overall track rate to increase by about 40%, which we think is manageable. And this, so I mentioned before that the L1 tracking is good for reducing the rates of triggers that we're already familiar with in the current experiment. But we also have the possibility, especially with displaced tracking, of introducing entirely new kinds of triggers. For example, a displaced track jet trigger, which has been studied in the context of a Higgs boson decaying to exotic long-lived particles. And you see in the bottom right plot that when we include displaced tracks at level 1, we can greatly increase the number of these kinds of events that we can collect for a given L1 rate. And then the displaced tracking can also help with electron tracking, which is challenging, of course, due to large Bremsstrahlung. So electrons can appear just like displaced tracks in the outer tracker if most of the Bremsstrahlung occurs before the outer tracker. And so as you can see in the plots of tracking efficiency versus ADA and PT, we get a nice few percent increase in the efficiency with the inclusion of the displaced tracking, which is a nice kind of bonus from including that. Then, of course, this has all been studied in simulation, but of course, the final algorithm has to be implemented in hardware. So it will be implemented as an FPGA design, and it's organized as a series of processing modules with memory modules between each step. Most of these modules have been implemented in Vivado HLS, which is C++ from Xilinx. The only exception is the common filter fit, which is largely implemented in VHDL. And then all of these modules will be connected in a top-level VHDL module. And then the actual the algorithm will run on hardware that's based on the ATCA platform, which is the CMS standard for HL-LHC upgrades. And so the board on the left is called Serenity. That handles the DTC processing that I mentioned before. And then the actual tracking algorithm will run on the Apollo board that's shown there. And we've already tested successfully multiple subchains of processing modules on these boards. So that brings me to my conclusion. So L1 tracking is a key part of the strategy in CMS for making the most of the data that we'll get from the HL-LHC. So the algorithm combines a road search for pattern recognition with a common filter fit. And simulations show that the algorithm will perform very well. And it's being implemented as an FPGA design mostly in Vivado HLS, but also VHDL. And multiple subchains have been already successfully demonstrated. So the focus now is on finalizing system specifications, including determining the feasibility of things like displaced tracking, and also demonstrating more extensive chains of modules in the hardware. So thank you.
Thanks, Andrew. We're out of time. I don't see any questions. I just wanted to remind people to also join the Mattermost channel for this session and maybe have a discussion there if you have further questions. Otherwise, thanks, Andrew. And we can move to the next speaker, which is Alexandre Zabi from LLR and École Polytechnique on the CMS trigger for HL-LHC.
Thank you very much, Petra. Can you hear me fine?
Yes, perfect.
Okay. Good afternoon, everyone. Let me just put this in. Can you see the slides correctly? Yeah?
Yes.
Okay, let me proceed. So, good afternoon. I'd like to thank the organizers for giving me a chance to present the CMS trigger for HL-LHC. So, I'll start with describing the context of triggering at HL-LHC. CMS experiment is equipped with a two-level trigger system with a hardware level 1 trigger, followed by a software high-level trigger. And I will describe to you the upgrade to both of these systems. So triggering at HL-LHC. So clearly, the HL-LHC upgrade program is an opportunity to achieve scientific progress. The machine itself, as it has been presented today, in its ultimate configuration presents very high luminosity and about 200 pileup. So we're looking at an integrated luminosity after 10 years of operation, which is about 4,000 inverse femto-1. So these key numbers have been used as baseline for all the TDR studies we've performed. So given the high multiplicity of particles, we're looking also at an upgraded an upgraded CMS detector with an extended muon system information on the calorimeters. Timing layer, and for the first time in a tracker, the availability of triggering information has been described just a moment ago. So given the amount of information produced by this detector, the whole trigger and DAC will be upgraded. So this really sets the context of triggering, defines the system requirements. So we'll keep our two-level triggering approach with level 1 hardware and a software HLT. We'll increase the bandwidth of level 1 to 750 kilohertz to maintain our acceptance for physics, increase the latency to allow us to include high granularity and tracking information for the first time. So fully reconstructed tracks available to us. The strategy is to exploit as much as possible the upgraded backend electronics where we can aid with particle identification and reduce the rate. We want to produce sophisticated reconstructed objects, which we want to correlate to achieve enhanced physics selectivity. We also want to expand our trigger with a scouting system, allowing us to scrutinize the data further. So all of this is very nicely presented to you in this level 1 TDR that has been approved and released a few weeks ago. For the high level trigger, we want to keep a rejection factor of 100, going to an output of 7.5 kilohertz. So that imposes a load on the amount of CPU power we need to deploy. The data throughput moves to 61 gigabytes per second. We want to have optimized reconstruction software, balance efficiency rate, and event size and timing. So the strategy for the HLT is really to benefit from modern processors, technology, and looking at the possibility of having an heterogeneous architecture combining CPUs and GPUs. You can already look at the interim document where you'll find more details on this, and the TDR of the DAC and HLT is coming next year. So for the for the level 1 phase 2 trigger requirements, it's not only about maintaining thresholds as they have been up to now in the phase 1. The level 1 trigger has to be ready to trigger on any unconventional signatures. So the system is really to be regarded as a scout looking into the HL-LHC data. As this translates into algorithm, we need to have algorithms which are as close as possible to offline. To have sophisticated trigger algorithm, we can use specific technologies, including ability to trigger on displaced objects like jets or muons, for example. We want to extend the system with a scouting system, which I describe here very briefly. So this is not a trigger, it's really a system that harvests the data at different stages of the trigger, or level 1 trigger at 40 megahertz, and basically reconstructs and provides you with physics objects you can use to scrutinize further the event, making sure that you didn't miss anything in the LHC data. So this really allows you to identify signatures which are usually unreachable through standard triggering techniques. In terms of the technological choices we've made for the level 1, we want to achieve global event reconstruction, but we're looking at an input that is 60, the order of 60 terabit per second versus the 2 terabit per second we had during phase 1. So that translates into investing into modern technology. We're looking at FPGAs, which have 8 times more resources and 3 times faster optical links. We've gone through the extensive use of the high-level synthesis, which allows us to produce FPGA executables based on C++ algorithm code. So we achieve a much faster turnaround. We can contemplate new ways of developing algorithms, like based on machine learning, for example. So we can do much more with the trigger now. And our advanced architecture is based on ATCA, allowing us to reach a robust, flexible, and modular design. For the HLT, we're looking at a rejection factor of 100, as I mentioned to you, and keep the timing below 500 milliseconds. In terms of reconstruction, the challenge includes looking at more complex detector data, such as the high-granularity calorimeter, for example. In terms of the average event processing time, we know that it increases with the instantaneous luminosity, but also with pileup, and we're looking at 7.5 times more input rate compared to today's system. Today's system is actually described to you in the center, where we basically have software event reconstruction and selection running in this HLT farm made of commercial servers. We have more than 4,000 CMSSW software modules that are running, and an average timing of about 264 milliseconds. So the requirements for the HL-LHC is, as I mentioned to you, is the extended computing power. In terms of reconstruction, we really want to optimize our software. And we're really contemplating the ability of offloading part of the processing to GPUs, which we can estimate today, and I will tell you more about this in a few moments, to 20% for the tracking and calorimetry. Okay, let me get into more details of the conceptual design and the performance of the phase 2 level 1 trigger. You have in front of you a functional diagram of that trigger. And we've reached that architecture by looking at an efficient distribution and processing of the trigger primitives from the subsystems. We provision appropriate resources and interconnections, and we retained enough headroom for future flexibility and robustness. So the key design feature of that system is this correlator trigger, which is you see in the center, that allows us to harvest all of the data and produce sophisticated algorithms. For the technological choices, we are looking at investing into generic processing engines, which pictures you see on the right side, and this is largely inspired from the phase 1 upgrade. We want these FPGAs to be loaded with less than 50% occupancy, and the overall latency of that system is targeted to be 9.5 microseconds to keep 20%, roughly about 20% of contingency. In terms of algorithms and menu, since we have the ability, the availability of tracking, and we also reconstruct the primary vertex from these tracks, we want to reach performance of our algorithm as close as possible to the offline ones, so having much sharper turn-on curve. So we also exploit the complementarity of the different flavors of objects we produce, like the standalone objects, using only subdetector information, track match objects, and particle flow objects. You can see some highlights of the performance, which I extracted from the TDR, and you can look further. In terms of the menu, we've done the full exercise, and the menu, which is equivalent to the phase 1 menu, looks at 346 kilohertz, so well below the contingency plan we have for the overall level 1 bandwidth. And adding about 100 kilohertz, we can have also extensions looking at expanding the physics reach. So if you want to know more about these algorithms and performance, I invite you to look at these two posters, which are listed at the bottom. I mentioned to you the global event reconstruction at level 1. CMS has successfully used particle flow in its offline analysis, along with a algorithm which helps us mitigate pileup, which is called PUPPY. And we said, so why not implement this into an FPGA? So the advantage of that is, as you can see on the right, the reduction, that reduces a lot the event complexity, keeping the core physics information you have in the event. You reach a much better response on your particle flow objects. So the particle flow candidates and PUPPY candidates are combined into offline objects you can use for triggering. We have successfully demonstrated the combination of pFlow and PUPPY in hardware, as you can see on the bottom right with this hardware demonstrator. A lot of the code, and it's important to note it here, is that it's been designed by physicists along with engineers. So we're looking at a very promising prospect for that project. So you can look at Dylan Rankin's poster on particle flow, which will be presented to you this week. Moving on now to HLT.
1 more minute.
Yes. So moving on now to HLT, we've historically wanted to have HLT running the same code as offline for many reasons. that has been positive to us. And in fact, we've been using general purpose CPUs as it was the case for other LHC experiments. With the demonstrator, which I'm mentioning to you here, which is called Patatrek, we really have a good estimation of how much we can offload to GPUs. And we are contemplating an offloading scheme of about 80% of our process for phase 2, okay? So we are planning to run this during run 3, gaining experience on running these GPUs, and also gaining experience on this heterogeneous architecture, which is promising for the future. In fact, given the fact that GPUs can do very complex combinatorics, you've heard of quadruplets and triplets today in the tracking, you know, so by performing this on GPUs, given that it's much faster and you can allow it to run online, you can improve physics performance, as is shown to you here, on the tracking efficiency as a function of the track PT, comparing with the current performance in black. So this comes with a very small price on the data throughput when you move the data from GPU to CPUs. I'm almost done on the summary, just saying that we offer solid solution on triggering and data acquisition for HL-LHC. The level 1 trigger is now, project has been approved, and we're moving forward with the construction. And for the HLT, we're looking at very nice prospect of this heterogeneous architecture, and you'll know more about this in a TDR next year. Thank you very much. Sorry, Petra, for being just a little bit late.
It's fine, no problem. Are there any questions about the CMS trigger? I don't see any hands. I had a question for so if you run now more things on FPGAs, how do you take into account changing calibrations that need to be updated and so on?
We have, in fact, in the phase 1 running, we've been able to do this in between runs, essentially, right? Because you want the conditions of the data taking during the run not to change. But I think during phase 2 that there should be a possibility to update calibration even during the run. And even if it's on FPGAs, you can certainly, you know, reconfigure registers as you go. This is a little bit acrobatic because you don't want your run to crash in any possible way and lose data. But this is certainly something I believe we can try to explore. But usually it's true that in a common, let's say, way of running, we've never really updated conditions while we run, but it is possible.
Yeah, especially if you move to maybe using some machine learning or so, even in the...
Yes, there is a good case, in fact, that we've developed in the TDR or even on an autoencoder approach, looking for new physics, let's say, or unconventional signatures that we don't want to miss, in fact. So there is a good case developed in the TDR as well.
Okay, thanks.
Sure.
Are there any other questions? If not, we can move on. Thank you.
Thank you very much for having me.
Gabriella Pasztor from Eötvös University in Budapest on the precision luminosity measurement in CMS.
Thank you. So I will present our plans for precision luminosity measurement with CMS at high luminosity LHC. Okay, so measuring luminosity is already challenging at LHC, but with high luminosity, the experimental conditions will be much harsher. And we already see in run 2 that in some of the precision measurements, our current uncertainty of 2% starts to be the limiting factor, being the dominant systematic uncertainty. Therefore, our physics goals actually require a better precision at high luminosity LHC. So our baseline goal is to achieve 2% bunch by bunch luminosity measurement precision real time, so online. This will assist both beam optimization and luminosity leveling. And then with final corrections and calibration, we would like to achieve a 1% precision, which will make luminosity uncertainty subdominant in most of the analyses. But of course, this requires extreme care and very sophisticated calibration techniques, as well as it gives stringent requirements on our phase-2 system. So if you want to read more, we have a conceptual design for the luminosity measurement that I linked here. Okay, so what is how an ideal luminometer looks like? So it provides a bunch-by-bunch measurement with sufficient statistics. So what does it mean? It means basically that in the VDM calibration, which has a low pileup condition, we should have enough statistical power in about 30 seconds to measure the beam parameters. And then we will need fine time granularity in physics runs and bunch-by-bunch precision of less than 1%. So this luminometer should be operated at 40 megahertz with all bunches equally sampled. And if we need a trigger, this should be unbiased by luminosity pileup, bunch location in the train. So basically something like a zero bias or random trigger. This data should be published with a short latency and with the timestamp precise to a given orbit. And ideally, it would have a perfect linear response from the VDM low pileup conditions to the 200 pileup physics conditions, very good stability over the full running period, and the uniform response both to single bunches and so-called train bunches where the bunches follow each other closely. Of course, there is no such thing as an ideal detector, which basically means that we need a mechanism to measure and correct for any nonlinearity, instability, inefficiency, or other response degradation, for example, due to the radiation damage. And one last thing that is very important is that luminosity needs to be measured also at the time when the central data acquisition system is unavailable. So it should be able to measure luminosity, for example, during LHC Run. So based on our Run 2 experience, we came up with a strategy that basically requires for our system design to have at least 3 independently calibrated stability and linearity tracked bunch-by-bunch luminometers, preferably using diverse technologies so that we avoid common biases. This gives us operational redundancy, as well as identification of mismeasurements and the good control of systematic effects. And we also saw that additional luminometers, even if they don't meet all the ideal requirements, are very helpful in case of problems, and they help us to get further insight into systematic effects, which is very important if we aim for a 1% precision. Also, alternative techniques like counting Z bosons could provide input. I will only concentrate actually on the first bullet here, and this task in CMS is the responsibility of the Brill project. So just an overview of the systems that we will use to measure luminosity in phase 2. You have already heard many introductions to our tracking system. So we will use both the forward pixel tracker extension and the outer strip tracker for luminosity measurement, as well as the Muon system and the hadron forward calorimeter. And we also design a standalone dedicated luminometer. So let's start with the inner pixel tracker, for which we use the forward extension, which is here. So we have experience from Run 2 with offline pixel cluster counting, as well as simulation results, which basically show that it has a very good linearity. And we will use the TPX luminometry with an additional 10% level 1 trigger rate. using independent luminosity triggers, and the data will be split in the pixel backend and processed in the dedicated luminosity board. And one of the rings, disk 4 ring 1, will be given completely to luminosity measurement, and it will be operated as a fully independent luminometer with the full level 1 trigger bandwidth and using a dedicated backend, as well as a dedicated control stream, so that the clock can be provided to measure the beam-induced background during LHC run. We are moving our PCC, the pixel cluster counting quasi-online in run 3. And this will also allow to get us experience with real-time operation, the out-of-time corrections online, as well as dynamic VELO lists. And the design actually allows that we count not only clusters, but 2- and 3-fold coincidences. And this will also be a very useful monitoring tool. The outer strip tracker, as you already heard, provides so-called stops, 2-fold hit coincidences at module level at 40 megahertz. And our simulation studies show that the outermost layer actually provides very linear response and very good statistical precision bunch by bunch. So we intend to use this. It only requires histogramming at the outer tracker backend. And then we can read out these luminosity histograms over the control network. So while this is not guaranteed to provide luminosity data outside of global CMS data taking, this will provide an independently calibrated high statistics measurement of luminosity. Already in run 2, we have the barrel muon track finder providing orbit integrated muon candidate rates. This is real time with a very excellent linearity and stability, and this is almost background free. At present, it's not bunch by bunch, and the integration period is longer. So basically for phase 2, we would like to make it bunch by bunch and using about 1 second time intervals. And there are 2 ways to do that. Count the drift tube trigger primitives at the backend, or we could, and we do, explore the 40 megahertz level 1 trigger scouting system. The run-free demonstrator provides access to the barrel muon candidates, as well as the global muon trigger objects with bunch by bunch histogramming. So the interesting thing is that this could be extended in phase 2 also to look at the track trigger or calorimeter primitives. We have already used as a main luminometer the hadron forward calorimeter, and we do not plan any major change for this. We have 2 algorithms implemented using dedicated lookup tables for luminosity measurement. One is based on occupancy, counting above threshold, and then the other with the better linearity is based on the ET sum. For phase 2, basically we have very extensive experience with the necessary corrections to improve linearity, but we still have to look at the mitigation of radiation damage. We have a parametric aging model for HF, and we also have in situ measurements using so-called emittance scans, and there is a small difference between the two, so this needs to be understood. And also we might need some tuning of the threshold for the occupancy method to avoid zero starvation, but still maintain good linearity at high luminosity. Finally, in 2019, we had a conceptual design review for BRIL in CMS. And one of the main results was that we started intensive R&D toward the development of a standalone bunch by bunch precision luminometer. For this, the main requirements are sub-bunch crossing timing and an asynchronous front end, as well as I mentioned, a completely independent operation from the rest of CMS. And we have currently 2 proposals in R&D. One is a Cherenkov detector, which would be placed on the CMS caster table in the forward region. and optimized for luminosity measurement and remote readout. This would build on our extensive experience with the HF luminosity measurement, but could use the latest front-end and back-end electronics. This is also similar to the ATLAS current detector. And then the other one is the silicon PET sensor-based detector with a fast digital readout and active cooling in the tracker volume. So basically, we have a very good experience with our fast beam condition monitor in Run 2. This is also a silicon and diamond-based detector. And for now, we need to evaluate the options for the fast asynchronous front-end chip. So with this, I come to my conclusion. So we aim to reach 2% real-time and 1% ultimate precision for luminosity measurement. This will provide prompt feedback to LHC and CMS operations and the best possible input for physics measurements. For this, we exploit the data from existing subsystems, from the tracker, from the Muon system, scouting, and also hadron forward calorimeter. We also develop a fully independent luminosity detector. And basically, this strategy will enable us to have free, ideal or almost ideal luminometers and 5 to 6 independently calibrated measurements. And we worked over the TDR in the second quarter of 2021, and then, of course, proceed toward production as well, and then operation in high luminosity LHC. Basically, there is a delay because COVID, but we are still quite on time with a lot of progress since the conceptual design. Thank you.
Thank you, Gabriella. Very nice overview. Are there any questions? Yes, Paula.
Oh, hello. Hi, thanks. This is really amazing what you plan to do. I just had a question about the pixels. What price do you pay in order to get this additional backend in order to allow this disk 4 ring 1 to be operated? And the reason I'm asking is, could you consider adding another disk, and then you could get an even more kind of high level object into your luminosity measurement?
So basically, the ring that we will use this disk for ring 1 is at very high eta. So this wouldn't give much to tracking. So from the physics point of view, using it for luminosity measurement is not giving any problem for other tracking related requirements. So if you say there is no price to pay, of course, the price to pay is that you have to build your own trigger board. You need to put in the development that is needed to operate this fully independently from the rest of CMS, basically.
Okay, thanks.
Any more questions? I don't see any. I had one. Is there any consideration to use at least maybe silicon hits from the HGCAL?
Not at the moment. We were actually looking at also at other detectors like the timing detector, but for now the baseline design is just what I basically gave here.
Okay. Thanks. Well, if there are no more questions, we can move to the next talk. Thanks, Gabriella. So the next speaker is Marko Mikuz from University of Ljubljana on the BCM prime system for abort and luminosity measurement in ATLAS.
Okay, hi there from the seaside to Prague. I never imagined Prague had a seaside, so now I know it has. Okay, so let me try to share. You see the slide?
Yes.
Okay, perfect. So thanks to Gabriella for illuminating.
Can you make it full screen, maybe?
Oh, of course. Now it went black with me.
Yeah.
Oh,
That's good.
okay. Here it comes. Okay, good. So thanks to Gabriella for making such a beautiful introduction into what luminosity is all about. So I'll be quite more specific about what we are doing on one of the lumimeters for the ATLAS experiment for the High-Lumi LHC. And in a way, it is an offspring from not a lumimeter, but from a protection system for ATLAS that we are also doing. Okay, maybe Lumi is by the way, or the protection is by the way, whichever standpoint you take. I think protection is, without protection, you might have no Lumi. Good, so it's dubbed BCM prime. So, okay, forget about the jokes about what the prime means, but it's surely the ultimate ATLAS beam conditions monitor, because after that, there will be no ATLAS. Okay, so what do we want to do? We shall provide a fast bunch by bunch safety system for ATLAS. I think that's the prime importance of this system. And then, because we think we know how to do it, we will on the fly do the luminosity measurement. And of course, if we can do the luminosity measurement the way we want to do it, we also get for free the background monitoring capability. Okay, so how do we want to do it? I mean, we're counting on a, let's say, 15-year history. We have a device which is dubbed BCM, and it is a fast device. It is asynchronous, so it just acquires signals at something like 2.56 gigabits per second, and it is always there. So, and now the question is, I mean, there's a lot of activity in the experiments themselves because of collisions. How do you tell what is background, what is collision? And the name of the game is you have to have a very good timing resolution. So by that, if you can tell what is out of time, so what arrives from upstream in the ideal location 6 nanoseconds before the collision, then you want it. Then you definitely know this is an upstream background. Okay, and now with having mastered that, you can do various things. Of course, the obvious thing for protection, you want to abort if that activity is above a certain threshold. These thresholds can be pretty high, we learned in due time. So, okay, I mean, you need to keep flexible for the threshold settings also in interaction with the machine. And as we want to talk and need to talk to the machine, the best is just to include one of their devices at the same location as you have your own device. This is the so-called beam loss monitor, BLM, using not the, of course, the gas ionization chambers, but some more packaged thing like a diamond. Then the second thing, how do you go with the Lumi and the non-collision backgrounds with that device? Now, for the Lumi, the main algo in this world is the absence of in time, so that means collision hits, which arrive in the ideal location 6 nanoseconds after the collision. And for that, you need a single MIP sensitivity, obviously. And you get the maximal statistical sensitivity if you do your math at something like the zero counting probability of 0.2, so 20%. This then translates with Brownian statistics to 1.6 hits per cell. And lucky enough, the minimum is pretty shallow in this space, so it's not that important. What is much more important, you need a robust device. Between 2 Vandermeer scans, that device shouldn't change a lot, and the changes you ought to be able to calibrate out. Now, the problem here, and especially in the High-Lumi world, High-Lumi LHC world, is that you have to cover the mu range from the tails of the Vandermeer scan to the ultimate luminosity, which is more than 4 orders of magnitude. Okay. Now, if we turn a bit to history, just to show you how important timing is. So we built this ATLAS BCM. You see the reference below. And it's based on a synchronous 2.56 gigabit second readout by Rocket.io of a Vertex FPGA. There's 4 sensors per side. They're quasi at the ideal location, 6 nanoseconds away from the interaction point. They feature 500 picosecond time resolution, and they are happily working in ATLAS since ATLAS turned on. Now, for the performance, of course, I mean, being an abort device, you have to provide post-mortem diagnostics. That was heavily debated with the machine people, and I hope they learned something from our diagnostics. We fired ourselves, let's say, a couple of aborts at danger level. So a couple is not 2. There were a bit more, but with, let's say, 90% of them, we can convince the machine that this was really something going on that they didn't catch. And most of them were UFO-induced close to ATLAS. Then we did beam background diagnostics, and you see, I mean, with such a timing resolution, you can even, this is log scale, you can really resolve on a single detector basis collisions from backgrounds, but you see those tails. So, you know, if that tail with a wider timing resolution gets gets into your background peak, then you lost the game. You see also the delta T, and you see, of course, we are bunch totally bench sensitive. So you see that, of course, in normal runs, most of the stuff happens in collisions, and there is a bit of side humps for both upstream backgrounds. For the luminosity measurement, we did particularly well, although we were not built for that purpose. In run 1, where we were upgraded to the preferred ATLAS Lumimeter online. But in run 2, we had stability problems, mostly because we had absolutely planned on no diagnostics, which is, of course, vital if you want to do proper Lumi. Okay, that's history. So now, what have we considered for the future? We obviously seen that we suffer from this two-faced Jason the God looking into 2 directions. So you're frustrated by this abort and Lumi incompatibility. For example, we were really forced by the machine to set our abort thresholds higher, but that would just mean abandoning the Lumi totally. And of course, the fast timing that is more abort focused lowers the signal to noise ratio, and that, of course, feeds back into the Lumi stability. So for the HL-LHC, we said, let's separate out. Let's build 2 fast devices from sensor to off detector, but still keep the commonality whenever possible. And of course, there's then this, not just building, you have to install it, operate it, and so on. So we are grouping this, nevertheless, of course, in a physical station as an object to install. So where can we fit? Now, the sweet spot, if you translate this 6.25 nanoseconds into distance, is at about 1.9 meters. And now we have 2 rings available that we could put in at 2 or 1.8 meters. That's still, but that's not an issue. Now, we want to move out to an appropriate R that you will see we can cope with the radiation environment, and that translates to an eta of 3.6. So we will occupy a separate ring in the ATLAS ITK, within the ATLAS ITK inner pixel rings. So there will be 4 stations per side. Looks familiar, like the old BCM. But the virtue of that location is, unlike the previous, we were out of the acceptance. Now we are inside the acceptance. So we will have tracks, plenty of tracks from pixels to calibrate the detector. And especially for Lumi, this is a very, 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 very good thing.
This is your 2-minute warning.
Sorry?
2-minute warning.
2-minute warning. Okay, good.
Yes.
Okay, that's the environment. Let's just say that the NEAL is 2 × 10⁻⁵, and TID is 200 megarad. And taking into account the safety factors, you have to multiply that by 1.5. For the sensors, we want PCVD diamonds because of their robustness, especially for the abort functionality. We plan on 3 types of sensors of various geometry. And the aim is to keep the capacitance below 5 picofarads. Now, some of the sensors will be 3D. I direct you to the relevant talk tomorrow. And of course, we are heavily working with RD42 to get the best diamond one can get on the market or under the counter today. Good. So for the front end, we have designed our own front end in TSMC 65 nanometers. The preliminary results are rather good. So we had 2 iterations, and we can boast with the peaking time, with the settling time, with the noise. And we have 2 channels on each of the or 2 options for each of the front-end channels. One is dedicated to the Lumi, which has a sizable gain, of course, and one is to the abort, where the dynamic range is really, you would think, excessive, but that's what people want. Okay, good. Now for the readout, we want to have as many things as possible on the module itself. So we want to digitize on the module. We have identified a suite which could do it. Although one of the ingredients, the Pico TDC, is probably not up to standards, but we will still try to test it and incorporate it. But if we have that scheme, we can read everything out on fibers. We have enough bandwidth. We have enough also downlinks so that we can operate the clock reliably. Okay, that's the conceptual design of the station. There's many chips on that station. There's about 30 watts per ring, which it's not for the sensor. Diamond needs no cooling, but for the rest, to keep thermal neutrality, we have to cool. Now the schedule, what do we want to do in this year? Plus, of course, the COVID delay that we are all faced with. We want to build 4 of the prototype modules of each of the flavor. And then assemble that and at least prototype that into a station. How far we go is a bit debatable. So for the work division up to now, it's mainly Ohio State and Ljubljana who are doing the work with the help of Manchester and the recent acquisition of Wiener Neustadt. And of course, we are part of the ITK Pixels, so we rely heavily on the help for the integration services, links, and so on. Schedule, you see it's 23 when the game is over. We have to be ready with our modules to install on the inner system of the ATLAS ITK. Good. That brings me to my summary. Dear Chair, I hope I was not overly overtime. So I presented you a fast protection and Lumi measurement device inside the ATLAS ITK. And we have passed many milestones, including also the formal reviews, which are a pain in the neck, but they bring added value. And the schedule requires us to be ready for installation 2023. It's tight, but I think it's achievable. So.
Thank you, Marko. We have time for one quick question, if there's any. I don't see any hands. Just a reminder, you can also go in the Mattermost channel and talk there, or use the chat here.
Or send me an email, or use my Skype, whatever you want.
Okay, thanks. Then we have one more speaker before the break, which is Davide from Max Planck Institute on the upgrade of the Muon trigger in ATLAS.
Hi.
I'll release the screen as soon as I get to, okay, good. Sorry. Where's the stop sharing?
I think you should be able to just override the sharing.
No, it tells me that another participant.
I know that. Okay, I'll just, can I kill the guy? Of course I can. I'll just quit.
Okay.
Now I should be able. Do you see my slides?
Yes.
Very well. So thanks for the introduction. I will speak about the upgrade of the ATLAS Muon trigger for the high luminosity LHC. Currently, the ATLAS Muon spectrometer is composed by 3 stations of RPCs in the barrel and 3 stations of TGC detectors in the end cap, and those are currently used in the hardware-based level 1 trigger. In addition to them, we have also 3 stations of MDT monitor drift tubes for tracking purpose offline, and from phase 1 we will have also the new small wheel installed before the magnet for tracking and trigger purpose. And if you are more interested, I would suggest you to attend the Friday session. For phase 2, we are planning to replace the RPC chamber in the inner layer with a new detector with increased rate capability. And for that, we need to also exchange in the small sector the MDT with the new monitor drift tubes with the small radii. And we have also a new TGC in the IL4 station, and we will rename the hardware-based trigger level 0. We need to make some major modification to the trigger and readout electronics in order to comply with the requirements from the level 0 trigger. So we will have a higher readout level 0 rate of 1 MHz and a longer latency of 10 microseconds. Also, we need to improve our trigger performance, obtaining sharper efficiency turn-on curves around the PT threshold. And we need to improve the fake trigger suppression. Therefore, we need the entire readout and trigger chain will be completely replaced for the RPC and TGC, and we will have a new end cap and parallel sector logic board. And finally, we will have a new MDT trigger processor board, which processes for the first time the MDT information at level 0. We should basically refine the track candidates coming from the 2 sector logics. The new architecture will be all based on FPGA devices. Starting now to speak a bit more in detail about the barrel sector logic, this board will receive the information from the RPC, which are read out by the new data collector transmitter ports that will transmit it from the RPC with full precision for processing in the barrel sector logic. Which gets in input also the information from the ATLAS Calorimeter to improve the trigger coverage. The algorithm that will be used to perform the pattern recognition with the RPC is still under discussion. We have at the moment 2 options on the table. The first one is based on the use of an evolution of the current algorithm. And is basically a coincidence algorithm that looks for coincidences in predefined windows And then we select a good candidate if it has at least 3 hits in 3 out of 4 chambers, or it's in at least in the inner or in the outer station of the RPC. This schema provides about 96% efficiency. The second option is based instead of the use of deep neural networks, and here we divide ATLAS into sides in pseudo-rapidity, positive and negative, and create a map of ETA station versus RPC layer. And then here a muon with an infinite PT is represented by a vertical line. In this representation, we can open our ternary convolutional neural network, which provides in the end 5 parameters, which are the transverse momentum and the pseudo-rapidity of the lead and the sublead muon, and the total number of muons that have been reconstructed by the algorithm. In terms of performance, both algorithms have been able to reconstruct muon candidates with the similar efficiency and staying within the latency requirement of 1 microsecond. And both are able to fit the chosen sector logic PGA, which is a vertex ultrascale plus. And we expect by the end of this year already a prototypes for the sector logic and the DCT boards. Now moving to the end cap system, also in this case, we will need to replace completely the front-end electronics in order to transmit now the TGC hits with full precision to the 48 end cap sector logic boards. That gets input also from the detector upstream of the magnet. So then is more with the tile and the IS78 MDT at RPC. And in order to reduce further the fake triggers. Then we reconstruct segments in the TGC, and finally we can measure the alpha orbital angle to calculate the transverse momentum of the muon, where alpha is the angle between the reconstructed segment in the TGC and the interaction point, the line connecting to the interaction point, and beta is the difference in angle between the segment reconstructed in the TGC and the one in the Musmo wheel. The algorithm that will be used for the pattern recognition in the end cap is divided in 2 stages. The first one looks for coincidence independently in the 3 TGC stations. Then we can retrieve the track parameters from a lookup table, which is indexed using the coincidence pattern. Also, this algorithm has been already implemented in firmware and is under testing using a science evaluation board with a similar FPGA to the one that will be used in the final sector logic board. It provides good efficiency, higher with the current scheme, with respect to the current scheme. And we expect in the end an output rate for a 20 GBPT threshold about 30 kilohertz from the TGC sector logic board. Now moving to the MDT trigger. Here we will divide ATLAS in 64 sectors, 32 in the bar and 32 in the end caps. And we will have then a 64 MDT trigger processor board that gets an input up to 3 trigger candidates from the sector logic, which are used to identify as a seed to identify the muon tracks using the MDT hits information. The first step here is the so-called hit extraction, where we look for hits which are compatible in time and space with the current sector logic candidate. And then we reconstruct muon track segments independently for each MDT station. Finally, we can combine the segment information to compute the refined muon transverse momentum of pseudo-rapidity and transmit back the track candidates to the sector logic and finally to the central trigger processor unit. In the end, this board will be also responsible for data acquisition. So in the case of the arrival of a level 0 acceptance signal, the MDT trigger processor should transmit its information to Felix for the final readout. We have 3 algorithms at the moment under discussion to perform the segment finding task. The first one is based on the use of associative memory chip, therefore is meant as a backup solution to the baseline FPGA system. And the other 2 are the Legendre transform, which is a 2D scan over the position and the direction around the sector logic candidate seed. And then we identify a segment candidate looking for the bin with the most populated bin in the array. And the third option is this compact segment finder, which is a 1D scan only over the position, using the sector logic candidate as a seed for the direction. Then we look for the bin in the histogram with the most, the highest content of hits, and we use those hits to perform a final linear regression fit that calculates the segment parameters. Once we have these segments, we can calculate the PT with 2 different methods, depending on how many segments we've been able to reconstruct. If we have 3 segments in 3 stations, we can calculate the sagitta. Or if we have just 2 segments, we can calculate the deflection angle. Then we can finally calculate the transverse momentum of the muon, taking into account also correction in phi and eta, because of the distortions of the magnetic field of ATLAS. In terms of performance, we observe with our simulation that the MDT trigger is able to increase the selectivity for muon PT around the threshold while keeping a high efficiency plateau. And at the same time, reduces quite a lot the output rate of about 50 or 70%, depending on the detector region and the PT threshold under consideration. We are also working on a firmware implementation of the MDT trigger chain. And but from the preliminary results, we can already say that we should be able to implement it with a feasible resource usage and stay within the latency requirement of 1 microsecond. So this brings to my conclusion. The upgrade of the ATLAS Muon spectrometer readout and trigger electronics is a major challenge for the experiment for the high luminosity LHC area. We will need to replace completely the front and back end electronics of the Muon trigger system. We will have access for the first time to the full precision hits at the trigger hardware level trigger time, and we will need to increase our latency and output rate. I've been speaking about the 3 main components of the level 0 Muon trigger system, which are the barrel and the end cap sector logic and the MDT trigger processor. We are working on several algorithms to perform the final trigger decision, but we can already say that from our preliminary studies that we should be able to get good performance and using with a feasible resource usage of the FPGAs. Thanks for your attention. If you have any question, I'll be happy to answer.
Thank you, Davide. Questions? I don't see any. I had one you said for the pattern recognition, the ASIC, that's just a backup. Is that, did I hear you right?
Yes, this is a backup, is a solution. So we are doing also, like say, a parallel demonstrator using the HTT hardware for that. And this is meant as a backup solution since the prototype that we are working on doesn't involve the use of AM chips, so it's just an FPGA system.
But if that works, then you don't have to invest in the AM. ASIC.
Exactly, yes.
Okay, thanks. Any other questions? If not, we reached the halftime of this session. We have a 15-minute break now, or 13 minutes since we're 2 minutes late. So see you again in 13 minutes for the second half. All right, so I think the coffee break is over. Welcome back to the second part of this session. The first speaker will be Michal Kreps from the University of Warwick about test beam performance of a torch prototype module.
Okay, hopefully you can see my screen fine.
Yes, perfect.
Okay, so I'm glad to be here and to talk about the results from a test beam for torch. And so I will start with the discussion of what is torch and why we need it. And if we look to the LHCb physics program, there are basically two basic ingredients which makes it possible. One is very good tracking, and the other one is to have very good particle identification. And this is currently provided by two rich detectors. And if we look here on the upper plot, what we see just the rich Cherenkov light coming as a function of momentum. And when the kaons or protons have something like below 10 GeV momentum, they basically don't produce any light. So for these low momentum tracks, currently we do not have really positive particle ID. So the idea is to add the large area time of flight detector, which would actually provide positive particle identification for these particles. And the idea is that we can sit with this detector at distance of about 10 meters from an interaction point. And when we look the time of flight over this 10 meters distance as a function of momentum, what we will find at about 10 GeV momentum, the difference between the pion and kaon arrival is about 35 picoseconds, which means that we need a per track resolution order of 10 to 15 picoseconds. So this is then provided. So idea is to use this prompt production of Cherenkov light as the charged particles pass through the quartz bar, and then the photons which are produced then propagate through this quartz bar via total internal reflection to the focusing block, in which they are focused by cylindrical mirror in one direction on the photodetector. And this 15 picoseconds per track resolution then translates to a required single photon resolution of about 70 picoseconds. So this is what we need to achieve to make it viable. So the photodetectors itself are custom developed square microchannel plate PMTs, which are developed by our commercial partner Photech in the UK. And what we have is a photodetector with active area of 53 times 53 millimeter square, which sits in a 60 times 60 millimeter square housing with a high granularity. So that it's built with 64 times 64 pixels, and we group in one direction 8 of them together, because the focusing, given how the focusing is done, we don't need that high granularity in one of the directions. So this is then attached to the electronics, which is composed of a NINO and HPTDC chips. And this basically provides us 2 bits of information, namely when the signal actually crosses the threshold, and then how long the signal is over the threshold. And this is what we are recording in the test beam, both of these parts of information. Okay, so the test beam itself was done at the CERN PS in the east area, where we used the beam of protons and pions of 5 and 8 GeV momentum. The results which I'm going to show are mostly from an 8 GeV momentum. And the setup is following. So we have at the far right, we start with the Cherenkov counters to be able to separate the protons from pions in a fragmented beam. Then we have 2 timing stations. One sits at the start of the area, and then the other one behind the whole setup at the end with about 11 meter distance. And this is something which defines our time when the particles actually arrive to our torch module. And we have as well the silicon telescope in front of this torch module to help us to track particles and define the beam of where exactly it goes and how exactly it looks. So this is our experimental setup. So the torch module, it's shown here. So it's about half size of the actual LHCb module. Its size is 66 times 125 times 1 centimeter cube. And in a test beam, which we did back in 2018, which was our last chance, we had 2 out of 11 MCPs connected and fully instrumented with electronics. So if we look actually how the image will look from a particle passing, so it will generate Cherenkov light and will give a typical cone or ring of Cherenkov ring, which will be effectively projected to the detector plane, with a modification that as the photons reflect on the side of the quartz bar, actually at that point, this ring is folded and just follows zigzag pattern over the MCP or photodetectors. Now, at the same time, as we are moving along the ring, the path length of the photons is changing, and therefore the time is slightly shifting on each of these pixels. So as we go from one pixel to next pixel in a ring. In a test beam which we had, I said, 2 photo PMTs, and one of them had low quantum efficiency. So most of the analysis which I'm going to show is from this MCPB, which had a higher efficiency, and we understand what was going wrong in various places. So we are happy to use mostly this one. So continue with the image. If we just take now, I'm just concentrating on this one MCP. If I just look to one single column in a horizontal direction and just look in a vertical pixel versus time, so what we see are these bands of the hits as the photons arrive. And these bands basically correspond going from right to having a direct light, which comes from a beam or track straight to the photodetector, and then having 1, 2, etc. reflections on the side along the longer side direction. And the width of these bands basically tells us something about the time resolution which we need to extract. So moving to page 9. Before looking to the time resolution, the first thing I want to discuss is actually checking whether we understand the photons, number of photons we are seeing. And so in this particular case, what we are comparing is the shaded histogram showing the data, and the 4 plots showed 4 different positions for the beam going from the top of the plate down to the bottom. So spanning almost 1 meter. And then the full histogram just shows the expectation from simulation, how many photons we should see actually at the given position and given track. And what we can see that besides actually this first bin where we say we don't have any photons or any hits in a photodetector, we do understand the number of photons pretty well. And so this is quite encouraging. Now I just remind people that this is really having just 2 MCPs out of 11, and 1 had low quantum efficiency. So in reality, with a full detector, we should see actually much more light than this. And if I look to ratio, the 2 actually simulation and data agree pretty well. So going to time resolution, then to extract this, what we do, we just look to basically residual or the distribution of the arrival time for photons when we look mostly to low number of reflections, and we just fit together all pixels at the same time and try to extract the resolution on each of the columns separately. And what we can see on the right plot again for 4 different positions of the beam in a plate, that when we are sitting close to the photodetectors, we are approaching or achieving order of 70 picoseconds bits as we expect. When we are sitting a bit further away with a beam from photodetectors, it's not yet there, but we think we to some extent understand what's going on in this case. So, and this is something where we can try to somehow decompose this resolution to 3 different components. One is kind of constant component, which is mostly MCP itself, plus bit of electronics. Then there is part which depends on the propagation time of the photons, and then there is some part which depends on number of hits in a cluster, so something about cluster size and readout enters the ear. And if we do this, we actually extract what's on the left-hand side, and we can compare to expected numbers on the right-hand side, and we see that this constant term is actually spot on what we expect. The other two parts are a bit worse than we expect, and we actually know by now that we can attribute this to how well we actually could calibrate electronics before the test beam and from the test beam data itself. So to actually check this, what we did some lab-based measurements in which we illuminate actually single pixel of this MCP with a fast laser, and having all electronics connected, so as we would have in a test beam, with only difference that the HPTDC is running in a higher resolution mode than in a test beam. We actually can look to signals how they come. It's a bit weird unit on the x-axis, but we can fit again this distribution of the 4 signals, where we really look to signals only of the same width, which controls the time vogue effect, and we extract the resolution of about 50 picoseconds, which is what we would expect in this particular setup. So coming towards the end, so how these things will look in the LHCb itself, we will have, I said, large area detector, so it will be like 6 times 5 meters square. When it comes to our preferred location, which would be between tracking stations and the Reach 2 detector. So it's about 9.5 meters away from collision point. And we did a detailed simulation, giant 4 simulation, to see actually how this would actually perform. And this is what I'm showing here. So really running the full simulation in upgrade 1 conditions for LHCb, and checking 2 different cuts on kind of DLL for separating kaons from pions, and we see that below 10 GeV momentum, we can separate them very well with low mis-ID rate, and even more for the proton and kaon, which is really a place where we can help a lot the current LHCb. So this is something which can really help. There is still some work to do, but we know that this would be one of the options to really improve the physics program across the board at LHCb. So coming to summary, so we had this successful test beam in 2018, and we are actually approaching the requirements of 70 picosecond single photon resolution, and we plan another round in 2021, so next year, which should be fully instrumented, and by that time we should have much better calibration of electronics. So we are confident that we can fully demonstrate that we can meet the requirements we need. And I will stop here. Thank you.
Thank you, Michal. Very nice talk. Are there questions? I don't see any. I was wondering, how did you select the quartz, the crystals? You didn't say anything about that.
This particular one was basically coming from a manufacturer, which I have to admit I forgot from who we got it. And it was a special deal where they actually wanted to test as well things and see whether they can provide something of this type. So,
okay.
Yeah.
But
I should have remembered. I might post who actually produced that.
Okay, yeah.
But one of the main points for it was that it's very highly polished.
Mm-hmm. Okay. Yeah, if you have more information, that would be interesting. Thank you. If there are no more questions, we can move to the next talk. So we're moving to even faster timing. First speaker on that is Chiara Rizzi from CERN on the high-granularity timing detector for ATLAS.
Hello, can you see my slides?
Yes.
Okay, great. So good afternoon. I'm going to present an overview of the technical aspects of the ATLAS High-Granularity Timing Detector. So as it has already been mentioned today, the high luminosity LHC data taking is going to start in 2027, but the installation phase is going to happen during the LS3 shutdown starting in 2025. And in the high luminosity configuration, we'll collect a huge amount of data, more than 3,000 inverse femtobarn, but this will come at the cost of a much higher pileup rate, which will go from mu equals 30 over N2 up to mu 200 during iLumi. That also means that major upgrades are required for the LHC experiments to have a good performance in this environment. And the phase 2 upgrade is exactly this upgrade that will prepare the detectors for these. So once we have higher pileup can decrease the detector performance in several ways. For example, if we talk about jets, we can have, for example, that pileup jets that come from pileup vertices, or also pileup contributions to Hart scatter jets. To fight these from the purely spatial point of view, the main handle that we have is the Z0, but its uncertainty, if we consider ITK alone, degrades quite noticeably with the pseudo rapidity, especially if we consider low PT. So at high luminosity with mu 200, we expect to have about 1.6 vertices per millimeter. So the ITK alone Z0 resolution is not enough to disentangle all the vertices. And that's where AGTD comes into play, providing the time information as an extra handle that can be used to identify the Hart scatter vertex. So AGTD will improve the ATLAS functionality in the forward region. It will be placed in a small space in Z of 7.5 centimeters at 3.5 meters from the interaction point. And it will cover pseudo rapidity with eta between 2.4 and 4. So a very forward region. On each side of the interaction point, it has 2 disks, so 4 disks in total, and it targets a time resolution of 30 to 50 picosecond per track, up to 4,000 inverse femtobarn. So each HGT layer is divided into 3 rings, and this ring structure has the advantage of allowing an easy replacement of the sensors at small radius that are the ones that will suffer from higher radiation damage. So we have that the inner ring will be replaced each 1,000 inverse femtobarn, the middle ring will be replaced each 2,000 inverse femtobarn, and the outer ring will never be replaced. These replacements allow to keep the total fluence that each sensor receives lower than 2.5 times 10 to the 15 neutrons equivalent per centimeter squared. And this way, the charge collected by each sensor is high enough, and the total ionizing dose on the ASICs is low enough for the AGTD to have a good performance. So the AGTD bare module is built by a large sensor of 30 times 15 pixels, which is bonded to 2 ASICs per sensor. The bare module is glued to a flex PCB and connected to a flex cable. And modules will be hosted on support units so that these will help the assembly process. Each HGTD layer has modules on both sides, and these modules on the 2 sides are partially overlapping, but the amount of overlap between the front and the back side module is decreasing with the increase of the radius. And this disposition of the modules makes it possible to have an average number of hits for each track, which is in the HGTD acceptance, that is of at least 2 hits. Okay, so moving to sensors that are, of course, a crucial element for the HGCB. The technology chosen for the sensor is the low-gain avalanche detector technology. This technology has been developed by CNM in Barcelona and has now been adopted by several vendors. So LGADs are N-on-P silicon sensors with a built-in multiplication layer. And it's this built-in charge multiplication that gives us the improved time resolution. The nominal HGTD sensor has 450 pads, and each pad is 1.3 times 1.3 millimeters in area. And this is in order to achieve low occupancy, and it has an active thickness of 50 micron. The sensors will be operated at a low temperature, so minus 30 degrees, and this will be achieved through CO2 cooling. So there are several vendors that are tested for the HGTD sensors. In particular, here we see results from FBK, CNM, and HBK. Other vendors are being tested as well, like, for example, NDL. We can see that it's established that we have sensors that meet the HGTD requirements up to a fluence of 2.5 E15 neutrons equivalent centimeter squared, which is, as we were saying before, the maximum fluence that the HGTD sensors will be exposed to. In particular, here we see that the collected charge we see the collected charge as a function of the bias voltage at which the sensor is operated. And we can see that this meets the requirement of being higher than 4 femtocoulomb, which is the requirement that we need for the ASICs to have a relatively low jitter. And we can also see that we meet the requirements in terms of per heat time resolution, which needs to be lower than 70 picoseconds. And so in general, we can see that we have sensors that even after irradiation can meet the desired performance. So LGAD sensors have been tested not only in labs, but also with beam tests. The test beam campaigns have been carried out at CERN with 100 GeV pion beam until 2018, and then in 2019 at DESY with a 5 GeV electron beam. And on the left side of the slide, we can see the results in terms of charge collection and time resolution for gallium-doped CNM sensor, which had been irradiated at 315 neutrons equivalent per centimeter squared, so even higher than the maximum HGTD fluence. And we can see that this sensor has a good performance in terms of collected charge and time resolution. Then on top of that, the test beam setup also allows to have a tracking system. And this allows us to measure the trajectory of the particles that leave a signal in the HGTD sensors. This way we can see exactly in which point of the sensor the track heat is located. And we can check the uniformity of the sensor efficiency. And we can see that also in this case, this sensor has a good uniformity. On the right side of the slide, we can see a summary plot, which is built using test beam data from 16 different sensors, and showing that the efficiency when operating the sensor at a certain bias voltage corresponding to the charge value that we see on the x-axis. And we can see, first of all, that all the sensors show a pretty universal behavior. And also that we have a good efficiency from collected charge higher than about 2 femtocoulomb. The LGAD sensors are read out by dedicated ASICs called Altiroc that will provide 2 times, the time of arrival and the time over threshold, together with other quantities related to monitoring and the counting for the luminosity measurement. At the moment, we have prototypes that are being tested and a full-size version, Altiroc 2, which will read out 225 pixels, will have this year the first submission for the engineering run. Altirocs are tested first of all in labs, and here you can see the results for test bench measurements with Altiroc 1. This plot here on the left shows the efficiency as a function of the injected charge, while this plot here is again as a function of the injected charge, but it shows the ASICS jitter. And looking at these two plots, we can see why we had to require that the charge collected by the sensor must be higher than 4 femtocoulomb to have, first of all, good efficiency, but especially to have a low jitter, as we can see how rapidly the jitter increases with the decrease of the injected charge. Here we can also see the performance of the jitter after irradiation. So here we have the relative jitter as a function of the dose in megagrays, and we see at about 2 megagrays, which is the maximum total ionizing dose that the ASICs will receive, we have an increase in jitter of about 10%.
You have 1 minute.
So, okay, thank you. So Altiroc modules are also tested in test beams, and here you can see the results for Altiroc 1 at the November 2019 test beam at DESY. In this case, the Altiroc 1 was bump bonded to a 5x5 HPK 3.1 sensor, unirradiated. The time of arrival for this measurement is corrected for the time walk, and this is done by studying the dependence between the time of arrival and the pulse amplitude, which you see on the plot on the right. The fit function in red is the one used for this correction. And with the time walk correction included, the width of the distribution of the time difference between the tested module and the reference silicon photomultiplier is 46 picoseconds, and which results in a jitter contribution of about 39 picoseconds. Okay, so we have this great technical setup. So how do we use it to improve physics performance? So this is slightly outside the scope of this talk, but I still wanted to briefly flash the impact that AGTD can have on the ATLAS physics performance. So the time information provided by AGTD can help contrasting the negative effects of pileup when it comes to object reconstruction and identification. And this is the case, for example, in helping with pileup jet rejection, electron isolation, or betagging. But we could also make other examples like MET or jet energy resolution. And another aspect that we should not forget is that AGTD will play an important role as a luminometer. And this is because, thanks to the high granularity that is typical of this detector, the average number of AGTD hits has a good linearity with the number of interactions, and this will allow to have a smaller luminosity uncertainty than the typical run-through values. Okay, so in conclusion, we have seen how timing information will be a key element to mitigate the impact of pileup in the challenging environment of the high-lumi LHC. The ATLAS High-Granularity Timing Detector will use the LGAT technology to improve the ATLAS performance in the forward region and to provide an accurate luminosity measurement. The AGTD technology and layout are optimized to reach a per-track resolution of about 30 to 50 picoseconds at the end of the lifetime of the detector. Sensors and ASICs for AGTD are being tested both in labs and with bin tests, and have been shown to be able to meet the required performance. The AGTD technical design report is undergoing the final stages of approval and will be available in the coming months at the references that you have here on the slides. And that's all from my side. Thank you very much for your attention.
Thank you, Chiara. We have limited time, but I see 2 questions. Maybe you can keep it quick. Jeremy?
Hi, one quick question. Chiara, have there been studies to identify if there are any processes that would cause anomalous signals when, for example, more heavily ionizing particles go through this kind of sensor?
So I'm actually not aware of these studies. That doesn't mean that they don't exist. So if you want, I can look that up and maybe we can discuss it afterwards.
Okay, and then I see Kazu.
Hi, I have a very quick question. Maybe I missed, but what kind of radiation did you use to radiate the detectors, the sensors?
So the sensors have been irradiated both with protons and neutrons. The ones that I was showing on slide 8 have been irradiated with neutrons, while for the Altirox study on slide 11, this has been irradiated with an X-ray at an X-ray facility.
All right. Okay. Thank you.
Okay, thanks. Let's also remember that you can post question in the Mattermost channel or in the chat here. So let's move on to the next speaker. Thank you, Chiara. Next speaker is Carrie Folandi-Petrillo from Fermilab on the CMS MTD detector and specifically on the NCAP timing layer.
Can you hear me?
Yes.
I think I am still waiting for Chiara to stop sharing.
Oh.
There we go. Okay, can you see my screen?
Yes.
Great. So I'll be talking about the development of the CMS MTD NCAP timing layer for the high luminosity LHC. I'll start with some motivation for precision timing at the high luminosity LHC, give an overview of the NCAP timing layer design, and present some recent test beam results from February. So to start with some motivation for precision timing, I think as Chiara described very well, timing can be used to disentangle pileup interactions. So if we think about the pileup that we've had in run 2 and we'll have in run 3, we've had on average 50 to 60 simultaneous PP collisions per bunch crossing. This increases to 140 or 200 simultaneous interactions at the high luminosity LHC. And you can get a sense of what a single bunch crossing might look like in this plot here, where pileup vertices are plotted versus the z direction and in time. So timing sort of acts as a fourth dimension and can help disentangle vertices which are overlapping in z. And this impacts nearly every area of physics performance, right? We need to be able to identify which primary vertex our objects of interest came from. And having precision timing at the high luminosity LHC will be really important as a stepping stone for future detectors at future colliders where we expect even more pileup. For example, at the FCCHH, we expect about 1,000 interactions per bunch crossing. In terms of the impact on physics, with the MIP timing detector, we expect about 30 picoseconds precision timing per track. With this, we can improve or maintain nearly every area of physics performance with respect to what we have in run 2 or run 3, despite the large increase in pileup. You can get a sense for how this might work if you think about the Higgs to ZZ channel. If we can identify correctly the pileup vertex that leptons came from, we have better efficiency for lepton isolation. And with many leptons in an event, that better efficiency translates to roughly a 20% increase in the effective luminosity for that process. And you can see the contributions from how the barrel timing layer would improve that efficiency, and the NCAP timing layer would improve that efficiency as a function of the Higgs rapidity. And this increase in effective luminosity is similar for many other Higgs and di-Higgs channels where you have multiple objects, which improve from isolation or B tagging efficiency, even tau tagging. Something else that's interesting is that timing can give us new potential for particle identification and long-lived particle searches. So that comes into play on this plot on the right here. You can use time of flight to get the beta of your particle and study this as a function of particle momentum, enabling proton and kaon identification up to about 5 and 3 GeV respectively, which is much better than we can currently do with DDX information. I think it goes up to about 1 GeV for each. So then the timing detector is designed to provide 30 to 50 picosecond timestamp for every charged particle or track in CMS. It's located between the calorimeter and the tracker. I have a sketch where that shows sort of where the end-cap timing layer sits in CMS. Because the end-cap timing layer has about 10 times higher radiation than the barrel, we use silicon detectors known as low-gain avalanche detectors, or LGADs. And you can see here on this side some schematics of the end-cap timing layer, which highlight some of the design. So we have 2 disks per end cap, and sensors are on each side of each disk, which gives you an average of 1.8 hits per track. We expect to be able to obtain 50 picoseconds time resolution per hit, which translates to roughly 35 picoseconds time resolution per track. We have about 8.6 million channels and an active area of 16 meters squared. You can see in this sketch here on the bottom where the end-cap timing layer sits on the face of the high-granularity calorimeter. And it covers an eta of 1.6 to 3.0, sitting about 3 meters away from the proton-proton interaction point. The ETL is in a very thin layer, which is about 4.5 centimeters thick, and we keep it at minus 30 degrees Celsius to reduce jitter-induced noise using CO2 cooling. So then probably the most basic unit of the detector are these low-gain avalanche detectors. As Chiara mentioned, these are ultra-fast silicon detectors with a highly doped P plus gain layer inserted between the PN junction. This gain layer gives you a relatively large electric field in a very small region, creating charge multiplication and moderate internal gain. So fast rise time, but low noise. And this gives us our precise time resolution. In terms of our design choices, these are all R&D motivated. Our active region or depletion region thickness is about 50 microns, and this choice was made to minimize the rise time while giving us sufficient charge or gain and very good gain uniformity. The pad size is about 1.3 by 1.3 millimeters square, and this choice minimizes capacitance, which impacts your time resolution and keeps your occupancy low, especially for high pseudo-rapidity. The sensor size is 2 by 4 centimeters squared, or 16 pads by 32 pads, and this helps optimize our wafer usage. The interpad gap is below 90 microns, and this gives us a fill factor or efficiency of greater than 85%. The time resolution after radiation is spec to less than 40 picoseconds up to 1.7 times 10 to the 15 neutron equivalent dose. And these parameters have been optimized for quite some time. But recent prototypes from Hamamatsu and FPK have been focusing on improving radiation hardness, increasing the fill factor, and studying these larger arrays. And you can see some more pictures of more recent prototypes from FPK and HPK. On this slide here, I just want to highlight some features of LGAD time resolution. So here I have a plot from HPK, several HPK sensors using a beta source as our source of particles. This data is taken at minus 20 degrees Celsius. And this plots the time resolution as a function of the collected charge. So the feature to notice is that the time resolution decreases with collected charge, but sort of plateaus at around 25 to 30 picoseconds. And this is sort of the floor due to fluctuations in your Landau ionization for a 50 micron thick LGAD. This is the dominant contribution at high gain, where we would typically be operating these sensors. At lower charge, the jitter contribution dominates a little bit more, and the jitter here is proportional to the electronic noise, capacitance, inversely proportional to the charge, that's why I decrease the charge, and proportional to the square root of the rise time. So just keep in mind that 30 picosecond floor. Then we need to read out our sensors, and we do this with our front-end ASIC. This is the end-cap timing layer readout chip, or ET-ROC. And the ET-ROC has a very important role to play. It has a delicate balancing act to follow. So it needs to have low noise and fast rise time to maintain its contribution to the jitter less than 40 picoseconds per hit. And it needs to do this with a relatively strict power budget of less than 1 watt per chip. The ETROC manages to do this with some interesting innovations. So the first is that it uses a single TDC for both the time of arrival and the time over threshold measurements that it provides. And it also has configurable amplifier modes using low or high power, where the high power might be very useful for the lower radii where those sensors experience more radiation. And you can see sort of a schematic of how the ETROC works. The plan for prototyping is roughly sketched out here. So the first prototype was ETROC 0. This is a single analog channel with a preamplifier and the discriminator. And I'll show test beam results with ETROC 0 later. Then we have the ETROC 1, which is adds the TDC and is 4x4. Then we go to the ETROC 2, which is 8x8 in full functionality. And the ETROC 3 is the final 16x16 chip that will go into the detector. All right, so now I'll show some results from a test beam in February. This is from the Fermilab test beam facility with a subset of the test beam team. We're sort of blocking the setup here. So we use 120 GeV protons passing through this setup here. This is the tracking telescope, and our sensors sit in a cold box here along with a time reference. And so for this test beam, we focused on taking data with ETROC 0 and HPK 3.1 sensors. You can see a picture of the board that we used here. The sensor sits right here. This is a simplified concept for how the board and the ETROC work. And we have two output paths, which we can use to study how it performs. The first is the sensor signal goes through a preamplifier, which we spy on with a buffer, and is sent through a second stage amplifier. I'll call that the amplifier output. This won't be in the final detector, but it's really useful for R&D and characterizing our signal shapes. The second output path is through a preamplifier and the discriminator. So this is what the TDC would see in the final detector, and this has a tunable threshold as well. So I'll call that the discriminator output path. And there we can study contributions from the sensor due to those Landau fluctuations, as well as the preamplifier and discriminator jitter, much like what we would see in the final detector. And there the spec to beat is time resolution less than 50 picoseconds. So here on the slide, I have the amplifier time resolution. We did achieve 30 to 35 picoseconds time resolution from pre-irradiated sensors, where we would typically be operating them, which is really exciting because it's quite close to that Landau floor. So here I think this is the best performing point we have with the amplifier output. This is roughly how we measure the time resolution. We take the timestamp with a constant fraction threshold of 20% and subtract off the time reference, the photek. And we fit a Gaussian into that distribution and take the width to be our time resolution. Here I have the time resolution plotted as a function of the collected charge. And you can see this for the two ETROC configurations, as well as at room temperature and minus 20 degrees Celsius. And here the takeaway is that we do get to very close to that Landau floor, and that at high power mode, we're 5 to 10% better time resolution than the low power mode. Then on the side, I have the discriminator time resolution. And so here we also have very exciting results. So for pre-rad sensors operating above that 20 femtocoulomb, we obtain a time resolution of 40 to 50 picoseconds with 100% efficiency. And you can see this is the efficiency measured as a function of X and Y. This is measured by requiring a hit in all layers of the Fermilab test beam telescope. And we achieve 100% efficiency within the sensor, even at the best performing time resolution points. And then this is the time resolution from the discriminator. This includes a time lock correction using the TOT as a function of the collected charge. You can see, that we reached that 40 to 50 picosecond time resolution, and we perform, like I said, 5 to 10% better with the high power amplifier mode. Okay, so to conclude, the high luminosity LHC high pileup environment motivates 30 to 50 picosecond precision timing layer. I highlighted a few aspects of the NCAP timing layer design and the R&D motivated design choices. And then I also presented some new results from the February 2020 test beam. These were sort of the first beam tests of prototype sensors in the front-end ASIC simultaneously. We achieved 30 to 35 picosecond time resolution with the amplifier output. and 40 to 50 picosecond with the discriminator, which are very excellent first results and within specs for the final detector. So we're very excited to continue testing as we get back into the lab.
Great. Thank you, Carrie. Very nice talk. I see a question from Kazu.
Hi, on slide 13, I just wanted to ask, how did you measure the time resolution on the left?
Yeah.
I mean, you say that you subtract a reference contribution. How was it actually done?
Okay, so so what we do for each one of these points is we take the timestamp of the LGAD and subtract it from the timestamp of the photek or MCP. We fit that resulting distribution to a Gaussian, and that fit is shown in red as an example. We separately, so I don't show this here, but we separately measured the photek time resolution to be 8 picoseconds. So then we take the fit value, which is shown in red, and subtract in quadrature the contribution from the photek. Does that answer your question?
I think so. Yeah. Thanks.
Mm-hmm.
Okay, any more questions for Carrie? If not, thanks again. And we can move to the barrel timing layer then of CMS. And the speaker is Nan Lu from Caltech.
Hi, I'll try to share slides. Can you see the slides full screen?
Yes, very good.
Okay, thank you very much. Thank you very much to the organizers for this great opportunity. I will talk, oh, sorry. Thanks for the organizers for the great opportunity. I will talk about the precision timing with the CMS MIMP barrel timing layer for the high luminosity LHC. So as Carrie has introduced, the CMS MIMP timing detector is composed of barrel timing layer, which is using LISO bars read out by silicon photomultipliers as sensors, and the ANCAP timing layer uses LGAP sensors. This detector will provide precision time measurements for minimum ionizing particles with a time resolution of 30 to 50 picoseconds. The timing detector will help CMS to meet the high pileup challenge at the high luminosity LHC. Due to that, the beam spot has a time spread about 180 to 200 picoseconds, which is largely uncorrelated with the Z spread. We will be able to use the time dimension to reject pileup. For example, the 4D vertexing, which uses both the position and time information, it reduced the vertex merging from about 15 to 1% for the 200 pileup scenario. So this pileup mitigation enhances the particle reconstruction, which can improve, for example, 10 to 20% gain in the Dihiggs significance. It also provides unique capabilities to the CMS detector with particle ID for low PT hadrons and enables mass reconstruction of the long-lived particles. As you can see in the top right plot, the reconstructed mass of the long-lived particle neutrinos at different t-tau scenarios. This kind of mass reconstruction will not happen without the timing layer. Okay, so let's see how this detector technology is like. So the BTL sensor is composed of LISO crystals read out by silicon photomultipliers. The LISO crystal is a very small LISO bar, about 3 by 3 by 57 millimeter. You can see a picture of the LISO matrix 1 by 16 on the top right. So we choose LISO for several reasons. We wanted to minimize the contribution of the stochastic fluctuation of the time arrival photons detected at the CPOMs. So this, we call it the photostatistic term. This is inverse proportional to the square root of the number of photoelectrons created in the CPOM. So in order to reduce this term, we wanted the crystal to have a large energy deposit of the MIMP in this crystal, and we also hope that crystals will have a very big light yield. So for lysos, the MIB deposit about 4.2 MeV in the lyso crystals, and the lyso is also bright. It has the light yield about 40,000 photons per MeV energy deposit. Also, the lyso has excellent radiation tolerance. You can see on the right, we measured the time resolution with 511 keV gammas from sodium-22 source before and after irradiation with 22 GeV protons to a fluence about 2 times 10 to the 13 inverse centimeter squared. You can see the time resolution is unchanged before and after irradiation within the 4% precision of the measurement. So the scintillation signal from the lysos will be read out by the CPOM. The CPOM is a compact, fast, and insensitive to magnetic field and relatively radiation hard. For BTL, we have chosen a CPOM active area about 9 centimeters squared. You can see a drawing of our CPOM array 1x16 on the right. This is an array on the ceramic package. The CPOM will be coupled to lyso bars with glue. This setup enables the light collection C about 15%. We also chosen an optimal cell size about 15 micron, which is a balance between radiation tolerance and photon detection efficiency. As you can see in the right bottom measurement, the dark current will reduce significantly when we decrease the CPOM cell size. The gain of the CPOM is about 1.5 to 4 times 10 to the 5th, and it has a photo detection efficiency, PDE, about 20 to 40%, as you can see in the bottom plot, different sensor prototypes and under different overvoltage. We have measured the BTL sensor performance before irradiation in the test bin. You can see a test bin setup on the right, showing a single lyso bar coupled with 2 silicon photomultipliers at both ends. The timestamp of the particle transversing the BTL sensor is a timestamp by combining the time measured by both of the 2 CPOMs on the left and right. You can see on the bottom plot, the timestamp measured by the BTL sensor with respect to the reference MCP detector is relatively a constant along the impact point of the MIB along the crystal axis. Yeah, as you can see in the black line combining the time measurement from the left and right sensor. The time resolution is also uniform along the crystal bi-axis, achieving 30 picoseconds, as you can see in the right plot in the black dot. So we have achieved this very nice performance before the irradiation. However, we need to mitigate the dark count rate from the CPOMs after irradiation. We expect the DCR to be about 55 gigahertz after about 3,000 inverse Winkelmann. So here are several ways to mitigate the DCR noise. First of all, because the DCR will decrease by a factor 1.8 every 10 degrees C, we will use the CO2 cooling, trying to cool the CPOM temperature during operation as low as possible. Conservatively, we will cool the CPOMs to about -30 degrees C, and it's possible that we'll further decrease this operating temperature to -35. We will also anneal the CPOM at room temperature during the shutdowns. As you can see on the top plot, with 2 weeks annealing, the DCR will reduce by a factor of 2 comparing to the no annealing case. And if we do further annealing, exploring the annealing of during full shutdowns, we'll be able to further reduce the DCR by about 30%. We will also try to optimize the CPOM operation point by reducing the overvoltage over the lifetime of the high luminosity LHC by reducing the overvoltage, we will reduce the dark-on rate and also reduce the gain and the PD in the CPM as well. So we need to find the optimal overvoltage. So we have studied this using irradiated CPM sensors and light, injected light. As you can see in the bottom left measurement, based on the signal over noise ratio, we have identified optimal obturation point of the overvoltage after 3000 inverse femtobond within the power budget. And also, we will have a dedicated noise cancellation circuit in our front-end ASIC to further reduce the impact of DCR on time resolution. So about the Taufir ASIC, this chip has several challenges. The reduction of DCR noise and pileup we discussed. It also has to cope with high rate and dynamic range variation, because we will reduce the overvoltage during operation, so there will be a decrease of photoelectrons in the silicon photomultipliers. It also has to meet the power budget, about 15 milliwatts per channel. We have two Taufir versions. Taufir version 1 is currently available and has been tested. You can see on the right plot the measurement of the Taufir performance with laser pulses mimicking the actual LISO pulses that we will be seeing at BTL. We achieved 21 picoseconds per single Taufir channels. By adding the LISO photostatistic contributions, we expect to have about 31 picosecond time resolution before CPM irradiation. So this is a very good performance achieved with Taufir version 1 already. With Taufir version 2, this is a new front-end design, and it will also have this DCR noise cancellation circuit. So we already had the first version of this Taufir version 1 chip received in May and is currently under testing since July. Okay, so then overall contribution to the time resolution, we have shown the photostatistics and DCR noise dominate the time resolution. And the electronics, digitization, and clock distribution are negligible comparing these two dominant terms. We have also looked at another effect that might contribute to the time resolution, which is the in-time and out-time pileup to the time resolution. So the in-time and out-time pileup means that we will have a constant flow of photons and neutrons in the BTL sensor throughout the operation of the LHC. We measure the average photocurrents induced by this effect, and we found the contribution to the time resolution is less than 10 and 2 picoseconds respectively for photons and neutrons. So this is negligible. So based on from the sensors to the modules, we will have modules designed that includes 1x16 crystal arrays made out by silicon photomultipliers. We use flex cables to connect the ASIC with the CPMs for the best possible signal integrity. And this module design also encapsulates variability of the dimension of the modules and simplify the tray assembly. So on the larger scale, we have the modules, and 24 of them will be a readout unit, and 6 readout units made up a tray. You can see a view of the BTL tray in the R5 dimension of the top plot. As you can see, it's instrumented inside the tracker support tube. This brings to the summary. In the phase 2 CMS, we'll have a new MIM timing detector with a time resolution of 30 to 40 picoseconds. And the barrel timing layer will be based on the technology of LISO crystals read out by CPMs. It will significantly expand the CMS physics reach at the High-Lumi LHC. So let's stay tuned to the beautiful physics brought by the timing detectors. Thank you.
Thank you, Nan. A very nice talk. Other questions? I wanted to ask, so you showed the test beam results with the CPMs and the chip. This is unirradiated, right? You said.
Yes, this is unirradiated.
Don't have any radiation results yet.
For these, we currently have several test beams. We had a preliminary study of the irradiated sensors in test beams earlier this year in February, and we will have more testing campaigns coming. So we are currently analyzing those results. So yes, we are studying this effect more detail with the irradiated sensors. Yes.
Thank you. Any other questions for now? Okay, if not, we can move to the next speaker, which is Jeremy Mann from University of Minnesota, talking about the HGCAL, the NCAP calorimeter of CMS. Okay, you need to stop share.
Yeah, thanks. Sorry.
All right. Thank you very much. So I'm going to give a quick status update and review for those who aren't familiar with the NCAP calorimeter of CMS for the LHC, HL-LHC. So why are we replacing it? We have an NCAP calorimeter now. The main reason is that radiation-induced darkening has been reducing the signal from the current NCAP calorimeters, which are all based on scintillation technology. So in the lower left, you can see the damage, it's permanent damage from hadrons in the CMS HGCAL, and you can see how as the luminosity is increasing, the relative signal in some regions falls below 1/10 or below 1%. This is actually only the permanent damage. There's actually also a dynamic damage, which provides an additional factor of approximately 5, depending on the instantaneous luminosity. Of course, the instantaneous luminosity for HL-LHC will be quite high, and so the light signals available from the crystal calorimeter and the NCAP will be very low. In addition, the scintillators in the NCAP hadron calorimeter are also seeing damage. So you can see the impact of this on jet resolution. This is the resolution considering only the HCAL signal loss. In this case, the ECAL crystals are assumed to be perfect, and you essentially have no response at all from the HCAL. And you're only looking at the photon contributions. When you then remove the ECAL system, we really wouldn't be able to see anything at all for jets, tagging jets in this case, in the NCAP without replacing a detector which can survive the higher luminosity. The other aspect, when you consider a design for a calorimeter in the HL-LHC era, particularly the way that CMS data analysis and reconstruction has developed, is we should take into account the concept of particle flow very directly. And so as we consider our calorimeter upgrade, we want to complement the CMS particle flow reconstruction technique, where we are trying to optimize the reconstruction and also, of course, pileup suppression by clearly associating the tracks and then clusters in the calorimeter to individual particles, which could be charged particles, in which case where there would be a track, or they could be neutrals, in which case there isn't a track, and we need to separate those clusters from those that are that are the result of a charged particle. One of the big advantage in the HL-LHC era is that, as you heard earlier, in the HL-LHC era, tracking will cover the full NCAP detector, and so we'll have tracking inputs to the particle flow process, and it's the job of the calorimeter to keep up with that. So the design of the detector that we're putting together to meet this challenge is based on silicon sensors in the high radiation regions of the detector and scintillating tiles with silicon photomultiplier readout in the lower radiation regions. So you can see in the lower right the arrangement of the detector, where in this green region we have silicon active materials, and then in the blue region we have a scintillator active material, which will reduce the cost. The entire detector is constructed out of cassettes, which are sort of wedges, which have multiple modules mounted on cooling plates with the electronics and some portion of the absorber. So this is quite a large detector, about over 600 square meter of silicon sensors and 30,000 modules, silicon modules, which have to be constructed, and 400 square millimeters of scintillator, which will be hosted on 4,000 boards. So I'm going to go through the status of several of these parts of the design. So as I mentioned, the detector is organized into cassettes that made up of a cooling plate with these modules mounted on it. The front-end electronics is located on the modules, and then readout control is through the engine wagon motherboard system. So you can see the hexagonal modules laid out on the cooling plate in the left. Those are the green hexagons. And those are connected together by what are called the wagons, which bring the signals from the individual modules to these engines, where is all the most complicated electronics, and the optical data links, which bring the data off the detector. All of this is mounted on a cooling plate, and there are also power converters distributed throughout the volume. In the simulator part of the detector, we have these 10-degree sections which contain the simulator tiles and the PCB underneath with the photomultipliers, silicon photomultipliers looking up into the tiles. So the silicon sensors that we're using, these are the first use of 8-inch wafer technology for large-scale HEP sensors. So you can see that you saw the hexagons there, and in fact, many of us who've worked on this project for a while sort of see hexagons in our sleep. We use the hexagons because they maximize the use of the wafer area, since the wafers are circular. And so far, these sensors are performing as expected. There have, of course, been some teething challenges because these are new wafer lines, but the wafers behave as we would expect. We have a comprehensive test program, including full sensor tests using a custom probe card. You can see a picture on the left, all the little pogo pins, which go up to probe the individual cells of the sensor. And then you can see how that's used on a facility in the lower left. And we are carrying out reactor-based neutron irradiations. You can see the guys setting up for that. And we're also studying process control quality structures that are located along the edges of the wafers that we're not using. You can see those actually in this picture. Those process quality control units sit along the edges of the wafer. But the main thing is the actual sensor region. Of course, we have a problem of trying to fit a cone and build it out of hexagons, which doesn't work perfectly. So to improve the filling along the edge, both the inner edge, where we have a circular envelope, and the outer edge, which is also circular, by using partial sensors, so not full hexagons. We could, of course, do that by constructing a large number of different masks, but that would be quite expensive. So what we've done instead is to define a common mask, which has multiple cut lines. And by cutting the sensor in different ways, we can obtain different partial sensors. So we can obtain a 3, for example, which is a very small sensor, or a 5, which is almost a full sensor. We can actually obtain those from the same single wafer by cutting in the appropriate way. So the modules then, once we have the sensors, are constructed from a base plate, an insulating layer, the sensor itself, and then a readout PCB, which is mounted on top. And these are all glued together. And then the PCB is wire bonded to the sensor. We have an automated assembly process using a gantry and a robotic wire bonder, which has been developed at the University of California, Santa Barbara. The goal here is, since we have to make 30,000 modules, this needs to be highly repeatable. And so we're replicating this procedure and this tooling to a total of 5 additional module assembly centers worldwide. For the simulator portion of the detector, the tiles themselves we produced using both injection molding, which is a very efficient technique, but doesn't provide the largest amount of light, and also machining of cast simulator in the regions where we have the highest amount of radiation damage. Those tiles will then be wrapped with a reflector called ESR, an automated wrapping machine that can adapt itself to the 25 different sizes of tiles that are required. This is a challenge beyond the technology that was developed, for example, for Khalees. We've also identified photodetectors, which provide sufficient signal to noise over the life of the experiment. So you can see a picture of some of these very small photodetectors here. And you can see how these individual tiles are laid out onto a tile board, in this case glued down. The tile modules are constructed by an automated pick and place process. We take those tiles, which have been previously wrapped, and we lay them out onto a circuit board, which contains the photodetectors and the readout chip and a few other components. So you can see how that process works. On the left, we have the gantry, the pick and place gantry, which can pick up tiles from the tray located at the back of the picture and place them onto the green PCB at the appropriate locations by using computer vision. On the right, you can see the first fully active tile board that's being worked on at DAISY. So you can see how it's being read out here through this cable. And the first single photo electron spectra have been produced with this readout chip, which is an important step forward in the operation of the detector. And we're looking forward to test beam operations coming up in September. Oops, sorry, left the photo. All right, electronics and motherboards. So the readout chip was received in late 2019. It's operating well, including the radiation tolerance. The version 3 with the full DAQ rate capability is under the final design. The concentrator ASICs, which are responsible for collecting all the data and winnowing out only the parts that are interesting, either for the trigger or for the readout path, are nearing completion. Will be submitted the trigger in the fall and the DAQ in the winter. And prototypes of all the key electronics boards are underway or complete. So the engines, in fact, photo was supposed to be here, but the board is actually still in the assembly house. I was expecting to have it back on Thursday last week. And then the wagons, which interconnect the modules. You can see the long green object here. That's one of the wagons, which connects to the engine, the small board that sits here. So those are all coming together, and we're going to be putting together a larger system to validate the overall electronics architecture as we proceed through the fall. In terms of the cassettes and the mechanics, of course, we have to build an absorber. So the Hadron absorber design is now in a very advanced state. So you can see some parts of that. There's an inner support cylinder, which is where the individual pieces of the absorber will connect, which provides a lot of the mechanical support. Then there's additional mechanical support for the thick steel absorber plates at the edge. So you can see the bolts that go in between the various layers, and also this tie rod that is required to connect along the angled region of the detector. So that design is in an advanced state, and production is expected to start next year. The cassette design and the process of its manufacture is also well advanced. So we've produced multiple prototypes of the cassette cooling plates for both the electromagnetic portion of the detector and the hadronic portion, including the section of the CEH, the hadronic section, which has the scintillator, which is the most complicated case. Those tile boards have all the components, for the most part, are on the back side of the board. And as a result, we have to cut holes or notches into the cooling plate to accommodate their physical space. So you can see an example of such a cooling plate here. This is a 20-degree version. And you can see the large number of cutouts that are present to support all the individual components that have to be supported. So getting all that mechanics correct is an interesting challenge.
1 minute left.
So we've also had good results from test beam. We had a test beam in 2019, which had 28 EM layers, 12 silicon layers of hadronic readout, and 39 scintillator layers from our collaborators from Calais. We measured electrons, pions, and muons with energies from 20 to 300 GeV, so over a wide range. And you can see we find excellent electron energy resolution, which also matches well with the Monte Carlo. We see good hadron resolution using the silicon portion of the detector. And you can also see the timing performance of the detector, which this detector should be capable of doing excellent timing for energetic showers as well, where the expected performance at the level of 50 picoseconds, is being observed. On reconstruction, I'm not going to say anything because actually Jingyu is going to talk next, so he'll tell you all about that. And so I'm going to move to my summary. This is the HGCAL is where the highly granular calorimetry is going to come to life, the energy frontier, building on many previous developments. We're vigorously prototyping towards the fully engineered design. Some things have been delayed by, of course, this virus, but the team has been working hard to advance those parts which have been less affected. And the system tests are now moving forward with the fully functional front end and moving towards the full engineering design review in 2021.
Great.
Thank you.
Thanks, Jeremy, for this very nice overview. Other questions? I don't see any. Could you comment maybe on should the scintillators here of the injection molded versus the cut? Can you comment on what are the advantages?
Right, so the advantages of the injection molding are very much in the area of cost. They're very inexpensive. The cost is in the mold construction. Once you have the molds, you can make a large number of tiles for very low cost. The problem is that the mixtures of scintillation dopants, which are compatible with that kind of production, you can't get quite the same level of concentration that you can when you're casting. So as a result, the cast scintillator is brighter. You get more photons per MIP than you get for the injection molded scintillator. And that's just an inevitable effect of chemistry, essentially in the end. And therefore, in the regions of the detector where the radiation will be the highest, and so we'll have the most noise in the photodetectors, we really need that extra signal that we get from the cast materials, which is why in that region of the detector, we would expect to use the cast material, even though it is more difficult to work with.
Okay, thanks. Are there any other questions? If not, yeah, we can move to the readout now. That's a talk by Jingyu Zhang from Florida State University on the construction of 5D information out of HGCAL.
So I think you can see my screen and my mouse, right?
Yes.
So as Jeremy already introduced, that HGCAL is a very innovative detector. It has a lot of capabilities too. So to be able to get the best out of it, we are actively investigating and developing reconstruction approaches. So I'm going to talk about 3 approaches here. So the TICO framework, the hierarchical density-based clustering, and the advanced machine learning approaches. So the TICO framework is our mainstream development, and these 2 methods are just something under study, and we are trying to see if we can get better results. So start with TICO. The TICO framework starting by reconstruct 2D layer clusters in each layer, and then use the 2D layer cluster as input. It reconstruct 3D objects using pattern recognition, and the 3D objects are called tracksters. Then we apply particle ID and energy regression to get the final results. So it is an iterative approach. The idea behind this is we first reconstruct simpler objects like E-gamma objects first, then we mask use 2D layer clusters, and then we move to more complicated objects like hadronic showers. So the CLUE algorithm is used to reconstruct 2D layer clusters. It has the following steps. So it first calculates the local density of each cell. The local density is defined as the weighted energy sum of the cell and its neighbors. And then we find for each cell the distance to its nearest neighbor that has a higher density. So one thing to mention here is that in these steps, the nearest neighbor query, we implemented this tiling data structure for computing speed up, and it is illustrated here. Basically, we cut the space in tiles, and for each query, we only need to look at the tiles covered by the searching distance. The third step is to define the seeds, the followers, and the outliers. So the seeds has to pass density threshold and some distance threshold, and the followers are everything that are not seed and pass another distance thresholds, and outliers are everything else. So removing all the outliers, we can put all together the seeds and its followers as clusters. This algorithm is very effective in rejecting noise, and it helps to reduce combinatorics for the next step. So the next step is pattern recognition. The pattern recognition here are based on cellular automaton. For each layer cluster, we open a search window in the following layers. And if we find a layer cluster in the search window, we connect them and we call it a doublet. And then the doublets are linked if they pass 2 angular requirements, and these 2 angular requirements are illustrated here. So the one is about the angle between the doublets and the track.
and another is about the angle between two doublets. So with all the doublets linked, we can create tracksters by collecting all the linked doublets from the innermost layer to the outer layers. So because the showers can be lumpy, especially for hadronic showers, we are using this in-out and out-in approaches. So these out-in hoops really helped us to solve the situation with lumpy showers. So because this is an iterative method, so the requirements vary in different iterations. The TCO is designed GPU friendly, and the clue part is already fully validated on GPU and achieves speed up in line with high Lumi LHC computing expectation. So some performance results. This is a single photon performance at 0 pileup. This is energy response, and this is relative energy resolution. The black is from reconstructible energy, and the magenta is clue clustered, and blue is TCO clustered. As we can see, the clue is working very well, and TCO is also able to cluster a large fraction of the energies, and for the resolution, TCO is almost comparable to the reconstructible. And for the hadronic showers, and it's the same as before. This is energy response and resolution. The label are also the same. Non-interacting means it does not interact with the tracker material. And again, clue is working well, and TCO is able to cluster large fraction of the energies. And looking at these resolution plots, the result is also very encouraging that TCO achieves less than 10% resolution at high energy. So finishing off with TCO, I'm going to talk about the HDB scan method. So this is a novel algorithm that is suitable for nested data. It takes reconstructed hits as input, and it estimates the density by calculating the distance between one cell to its nth nearest neighbor. So in this calculation, only cells located within 10 layers can be considered as neighbors, and the distance metric is taken as a Euclidean metric in eta 5 space. And once we have all the densities, we can scan over all the density to construct this cluster hierarchy. So the cluster hierarchy is illustrated in this dendrogram. The lambda value is 1 over epsilon, and width and the color both represent number of points. So if we look at here, we see that at a very low density, every point merge to form one cluster. And at some point, it's split to 2 clusters, and in another level, we can get this cluster splits to another 2, and we keep going, and we find the cluster hierarchy. The next step is just to extract clusters from the hierarchy. So the method we are using now is we calculate the area in this dendrogram for each cluster, and if the mother has a bigger area than the sum of the children, we will select the mother instead of the children. So this is done to help avoid cluster splitting. And you can see some event displays of the reconstruction from this method. So this is at 0 pileup, 2 charge hadrons are injected, and this is at 200 pileup. This is a single charge hadron was injected, and this is the same hits of the injected charge hadron, and this is the reconstructed clusters. It's only shown in a small window of the detector, but we can see that we can reconstruct the most dense part of the signal hadron, and as well as we can identify all the hard particles from pileup interactions surrounding the signal. So looking at more results, this is reconstructed energy distribution from HDB scan in both 200 pileup and 0 pileup. So this is energy equals 20 GeV sample at very high eta And this just corresponds to like PT equals 3. So this should be very difficult to reconstruct, but we still see a peak structure here with some tails, of course. And as the energy goes up, it's getting better and better. So this initial try shows that this algorithm is very powerful in terms of separating showers at a very crowded environment. So besides the method that rely on pattern recognition or clustering, we are also investigating end-to-end machine learning approaches for reconstruction in HGCAL. All these approaches are based on graphic neural networks. And the benefit of these graphic neural networks are that they are suitable for data with irregular geometry, like the data we collected from the HGCAL. So the idea of these graphic neural networks is that they use the information of the cells as input, and it learns the relations between the cells. As an example, so if we have a two-label output, signal is noise, we input for example, the coordinates of the cells, and what we get is the relationship between all the pairs of the cells. And it gives like if it is a signal-like relation or it's a noise-like. So some results. So this is an illustration in multiple particle gun sample, and this is something from a tau jet sample. And here we are showing the ratio of the reconstructed and the reconstructible. So from this, we can see that the neural networks are doing a pretty good job, and we can get good energy resolution from these neural network approaches. So in summary, we have put TICO framework in place. The initial results are very encouraging, and it already has excellent computing performance. Various R&D activities are ongoing. In these areas like energy regression, particle ID, pilot mitigation, etc. And in these areas, we are considering using advanced machine learning techniques. And besides the TICO framework, we are also looking at other alternative approaches. So by doing all this, we hope that we can deliver a reconstruction algorithm that does not only maintain the current performance, but also improve for the high-lumi LHC. Thank you very much for this interesting talk. Other questions? Don't see any. Can you comment maybe if you compare with let's say the current reconstruction of HGCAL, time-wise also, how does it perform? Does it take a lot longer at the pileup of 200? So the current, if you mean if the current is a TDR, then the TICO is much better than TDR. Okay, but just if you compare even with the current detector, so time-wise, how long it takes to reconstruct a detector? Now we have all these channels and a lot more pileup. So for current detector, I don't know the number, but I can look it up. Okay. Thanks. Are there any other questions?
Yeah, hi. I had a question about this graph neural network. So you said it learns the condition, well, it uses the cell parameters and learns conditions about the system. So is that something that is dynamically done, or you train it at the beginning of a run, for instance, and then you keep certain parameter conditions, or you redo the training?
This we don't know yet. We have to see how it's. We need to fully validate this before like operation, of course. So we need to see if we need to train
trim once a while when detector condition changes. But
right, yeah. Okay,
yeah.
thank you.
So right now it's only initial results.
Okay, if there's nothing else, thanks. We can move to the next speaker, which is, I think it's Sven, right? I think you wanted to switch the order. Right, I think it's Daniele's first. Okay. Not mistaken. First on the general CMS talk.
Okay.
So Daniele Fasanella from CERN on the CMS Muon spectrometer upgrade.
Okay, you can see the slides.
Yes.
Okay, so I will talk about the CMS Muon spectrometer upgrade. So the CMS spectrometer covers the barrel and the end cap of CMS and uses different gaseous detector technology. It showed excellent performance at LHC in triggering, identification, and the reconstruction of muons. And I suggest also to follow the talk from Carlo Battilana about the performance of the muon reconstruction identification in the last runs. So moving towards high luminosity LHC, this will be a very challenging environment for the muon spectrometer, in particular for the new peak luminosity and the extended integrated luminosity, which will be 10 times the LHC design value. In order to cope with the new operating condition and also extend the physics potential of CMS, we are, first of all, installing a new detector, so GEM and improved RPC in the forward region to extend acceptance, resolution, and redundancy. We are also upgrading the existing detector technology. And finally, we are testing overall the system for the longevity for the new expected integrated luminosity and operational time. The phase-2 upgrade for the muon spectrometer has already started. In fact, it is in the main critical path of the long shutdown 2 and will be completed at the end of long shutdown 3. So for what regards the drift tubes, so the drift tubes, which are in the barrel, their front-end signal are processed by the mini crate, which is a complex system of board which handles trigger and readout. This system will not be able to withstand the expected background at high luminosity LHC or the maximal new level 1 trigger for CMS. For this reason, we are deploying a new electronic, which is based on only one type of board called the UBDT, which implements on FPGA the time to digital converter, and it will have improved performance, radiation hardness, and will improve the long time maintenance, and will be able to comply with the high luminosity LHC requirement. With this new design choice, all the trigger logics moves to the backend from the chamber itself. This will have more flexibility in combining the hits which are coming from the DT and RPC system, and will give us also higher efficiency using more than just 4 layers for the trigger primitives generation. The installation of the new system will be performed in LS3. So as we said, we have a new opportunity to develop trigger algorithms in the backend. Up to now, 2 approaches are being studied. Both starts assuming straight line tracks within the chamber and at least of triplets of layer priors within a super layer, which is a group of 4 layers. One of these algorithms relies on the mean time properly and does fitting using exact formulas. And this has already been implemented on FPGA and operated in the slice test demonstrator. And there will be also a poster dedicated on this algorithm by Leon Olgado. The other is based on the majority mean timer and the compact-UD transport methods, and it is histogram based. All this algorithm has been measured with simulation and also with run-2 data. We have done also stress test scenario with up to 200 pile-up collision for bunch crossing. And overall, both has good result. They are as efficient as the present system in the new condition and also improve spatial resolution. So I was talking about this demonstrator. In fact, during LS1, we have been instrumented a sector of the DT system with the prototype of the OBDTs, and it is being operated with a full phase 2 electronic demonstrator, which is implemented on phase 1 hardware. We have done different setup in different stations with different goals. So in 2 stations, we have done the full integration as in phase 2 with only new electronics, while in 2 stations, we are running legacy and phase 2 chains in parallel, thanks to the splitting of the signal coming from the front end. This system has been successfully operated since summer 2019. You can see we have a very good results in comparing old and new system. Also, we will reinstall back the legacy system in the MB1 and MB2 chambers, but we will keep, nevertheless, OBDT running in run 3, which will receive this splitted front-end signal in order to allow the test and development of phase 1 and 3. For what regards longevity is being tested at the GIF++ SAM facility, which give us a realistic environment because it has photons which has an energy which are similar to the neutron-induced photons in the experimental cavern, and allows a long period of irradiation in order to study aging. Additionally, we have also a period with a high momentum muon beam to allow checking the detector performances. This facility, it has been also extended in 2020 to allow more space and have a low intensity area, which is very good for DT. For DT, we have irradiated in the last year 2 layers in an MB2 chamber. And what we have seen is a strong decrease of the gain due to the deposition of material on the anode wire. This will have an impact on the sync-light efficiency with a reduction at the end of high luminosity LHC period around 75%. But this is an efficiency will be, first of all, only in the most exposed chamber of the detector, so it's only 10% of the detector. And the impact is reduced at different level. First of all, because we have multiple layers in the DT chamber. So out of 8 layers in the RF direction, we need just 3 to build an offline segment. Also, with the handling of the TDC in the back end, we can use new algorithms to reduce the impact of this reduction in efficiency. And also, we have that the CMS Muon system is highly redundant. So we have also it coming from CST and RPC detector. So in the end, this loss of efficiency has only a marginal impact, as you can see in the plots here, on the overall standalone muon reconstruction efficiency. And finally, to reduce the neutron background on the top of the detector, we are installing in LS2 a shielding made of layers of borated polyethylene and lead, covering the top of the 5 wheels of CMS. Moving to RPC, also for the RPCs, we are talking mainly on an upgrade of the electronics. We need to replace this obsolete rad-hard component and an aging system, which is the RPC-like system, with FPGA technology. In this new system, the radiation mitigation is based on triple modular redundancy and internal scrubbing techniques, which comes from Xilinx. And we plan to scrub the entire FPGA with a rate which is much faster than the rate of CO in the balcony. Also, this new system will let us move from the 25 nanosecond sampling that we are now to recovering the intrinsic RPC resolution. So to have a TDC timing resolution up to 1.56 nanosecond. And also we are replacing control diagnostic and monitoring, which is now based on a combination on copper cables and fibers, to a new slow controller, which is a much higher also available bandwidth. Also for RPC, we are studying the longevity as GIF++. So we have 2 chambers which are continuously irradiated and 2 which are used as a reference. These chambers are from different period of production. And we have already integrated almost 80% of the expected integrated charge at high luminosity LHC, and we have monitored different parameters. So we can see that the total current and the noise are almost stable after collecting 650 microcoulomb per centimeter square, and the average noise rate is quite small. Also, we can see that there is no shift in the efficiency curve versus time up to a background rate of 600 Hz per centimeter square. Another important point for the long-term use of the RPC system is the fact that the gas mixture in the RPC contains a greenhouse gas, and there is a strong commitment from CERN to reduce greenhouse gas emission, and also there will be a limited production worldwide in the future. So we need a solution for the long-time operation of this detector. So what we are doing is, first of all, to use a recirculation of the gas in the system in order to use only a small fraction of the gas. Also, we have a recuperation system in order to recover the greenhouse gases from the exhaust, and we have already a working prototype. And finally, we need to reduce the gas leaks. In fact, we have at some point 82 bar RPC chambers which were leaking. For this reason, during LS2, we have extracted almost 50 of these chambers, which are together with the DT, and we have repaired them. And we also are ongoing studies on alternative for the gas mixture. In the forward part,
1.5 minutes.
Okay, in the forward part of the detector, we are also planning to install this improved RPC, in which we will have an increased rate capability by a factor 3. This will be done lowering the electrode thickness, decreasing the gas gap thickness, and lowering also the electronics threshold. This improved RPC, we will have also a 2D measurement because strips are read out from both ends. We are already installing the services in LS2, and the installation will be done probably in a year-end technical stop before LS3. Now, just 2 words about the CRC. So we will have a talk just after me. So also in this case, the upgrade is mainly on the electronic and will be explained by Sven just after me. And also the gem upgrade. For this, there will be 2 dedicated talks, one by Giovanni Mossellin and one by Elizabeth Storling. And the important point is that the upgrade with these 2 new detectors, so electronics and new detectors, will give us the possibility to greatly improve the forward part of CMS, because we will be able to produce CSC plus GEM super primitives, and so improve the segment funding efficiency, disentangle the ghost in the CSC, and improve the muon direction within a single station. So in summary, the CMS muon system is ongoing a huge upgrade toward high luminosity LHC with the addition of new detector and a major electronic upgrade of the existing detector. This will give us the ability to withstand the high luminosity LHC environment, and also improve timing, extend ETA coverage, improve triggering, and improve radiation tolerance. And a large part of this upgrade will be already in place for run 3, in particular a first ring of GEM, the on-detector electronic refurbishment of all the CSC system, the services for the new IRPC, and also the DT Phase-2 demonstrator.
Great. Thank you very much for this nice talk. Other questions? No, people are getting tired in Europe. Huh? Can you maybe comment on the trigger capabilities, like let's say for muons, the PT threshold or so?
Yes, as you can see, so here, for example, in this the last slide, we have some plots from the level 1 TDR. So you can see that we are able to keep the same efficiency that we have now in a much worse environment, in particular in the forward region. And this you can see in particular from the rate of the L1 muons. So you can see that with EMTF, which was the phase 1 system, this would have grown exponentially with the pile-up, while with the new EMTF++, which integrates this new electronics for CSC and the GEM and IRPC on the forward region, we are able to keep a linear increase of the rate with the pile-up. And this will give us a lot of potential also for physics,
Great, thanks. Any other questions for Daniele? Okay, doesn't seem to be the case. Then we can move on to Sven's talk. So next speaker is Sven Dildig from Rice University on the upgrade of the CMS cathode strip detector.
Right, okay. So I'll share my screen. So you should be able to see him. Maybe I can maximize.
Yep, looks good.
Okay, so yes, so this is the upgrade. This is a talk on the upgrade of the CMS CSCs for the HL-LHC. So quickly on the CMS Muon system, as explained in the previous talk, there are 3 different complementary systems. There's drift tubes in the barrel region, cathode strip chambers in the end cap of CMS, and there's resistive plate chambers, which cover both barrel and end cap up to an ADA of 1.8. And as part of the phase 2, all these detectors will be upgraded, but also new ones will be installed, in particular GEM detectors, but also IRPCs in the forward region. And so on this lower left picture, you kind of see the layout of CMS. At least one quadrant shows barrel covers DTs and RPCs, and the end cap you have CSCs and RPCs. And so these chambers, particular CSC chambers, are trapezoidal. And on the right, you can see a close-up of the ME+1 disc, which has 3 separate rings with CSC stations. Okay, so let's move to the second slide. So this is briefly on how these cathode strip chambers work. So these are trapezoidal chambers, multi-wire proportional detectors, and they each have 6 gas gaps, or 6 sensitive layers rather. There are 270 CSCs installed in 4 stations in each end cap for a total of 540 chambers. And each chamber has a finely segmented readout, both in cathodes, strips, and anode wires. So they read out your local phi position and your ADA position that you can use to reconstruct tracks. They have a good time resolution of about 3.5 nanoseconds and a good position resolution between 50 and 150 microns. And so these chambers operate as follows. So as a charged particle passes, the gas mixture, which is an argon CO2 CF4, electrons are released from molecules. The amplify in a strong electric field, and an avalanche is induced. And so these avalanches are read out separately on the wires and on the cathodes, cathode strips. And so you have wire hits, but also cathode hits. And so then they're processed with the on-chamber electronics. And so more on that on the next slide, where covers briefly the electronics design. So on the one hand, there's wire hits. So those are read out by anode front-end boards. So that's the gray box there. The other hand, there are cathode hits. Those are shown in these blue the purple boxes, read out by cathode front-end boards. And so anode hits and cathode hits are processed separately and then collected first in the anode local charge track board, which is this pink thing, and then processed ultimately with this trigger motherboard, which produces the actual trigger of a chamber. So that's one of the most important ones in this system. And there are a few other boards, such as the data collection motherboard, which is interfaced with the CMS data acquisition through this DDU. And there are a few other boards, like a low voltage distribution board, and then boards that provide other services. And so this is part of the phase 2 upgrade of the CSCs. So the high luminosity LHC, that's also not new. So the LHC will be upgraded to the HL-LHC during LS3. So we'll have about 3,000 to 4,000 inverse femtobarns of data over 10 years. Instantaneous velocity increases by about a factor of 5 to 7.5. And so obviously, with that amount of data, we'll need new trigger and data acquisition systems to handle the data in a ever harsher radiation environment. So in particular, these systems need to be able to cope with 750 kilohertz of level 1 trigger rate and the new latency of 12.5 microseconds. So they all need to be adapted to accommodate the new features. And so obviously the C system will have to be upgraded to cope with that. If not, then we would see large buffer overflows in CFEP. So those are the boards that process cathode hits in a 4 region. That's where you have a lot of background from being close to the beam line, in particular ME21. So that's one of the stations that is very close to the beam line. That would see a near 100% loss in data without an upgrade of the CFEBs. There's also certain memory limitations in all the ALCT FPGAs, so that needs to be upgraded. Data motherboards have insufficient bandwidth. Certain components are not radiation tolerant. So all that motivates the upgrade of the CSC electronics. And so this is a big part of the upgrade program. CSC electronics will be upgraded during LS2 and LS3. So there'll be about 1,400 new electronics boards that will be installed. But also trigger data will be sent from GEM detectors to CSCs via optical links in stations 1 and 2. And in addition to new electronics, CSCs will have to be operated with environmentally friendly gas mixtures, which is also quite challenging. So on the next slide, it shows you briefly about the timeline. So as I said already, the upgrade spans both LS2 and LS3. So LS2 is ongoing right now. And during LS2, we'll see some necessary on-detector refurbishments on detector electronics, such as the DC FEBs. Well, CFEBs become DC FEBs, which are digital, the front-end boards. ALCT boards will be upgraded. Low voltage distribution boards. Trigger motherboards become optical trigger motherboards, and a few other things will be upgraded as well. And then LS3, that's where we'll only need access to peripheral racks. So in LS3, the data motherboards will be upgraded, and also certain backend cards which provide the link between CSC and the CMS data acquisition system. And so in all, at least for LS2, there are 4 separate work streams which focus on, for instance, ME11, plus side, negative side, and all the other ME chambers close in the inner ring. Again, positive and negative sides. So that's how you get to 4 streams. And so these 4 streams span 2019 and 2020. And so below it shows the schedule for the second half of 2020. So a little more on that later. So let me quickly walk through the LS2 electronics upgrade. So like I said, one of the things that will be done is the upgrade of the anode local charge track boards. So here we'll have newer boards which have newer FPGAs, Spartan 6 FPGAs, which have 10 times more memory, more logic, and are much faster. The cathode front-end boards will be improved for the inner ring chambers. So here, the cathode front-end boards will be replaced by digital versions, which are all radiation tolerant. They have larger buffers, they have fast flash ADCs, and Vertex 6 FPGAs. And also the low voltage distribution board we upgrade to provide more power to those, to the ALCT and the CFEB. Also going on in LS2 is the upgrade of the trigger motherboard. So here, a copper version, so to say, will be upgraded by upgrade to a optical version. We'll have optical links instead of copper links. And the boards will be based on Vertex 6 FPGAs. They have a lot of computing power and logic and such. And then one final thing in LS2 is the upgrade of the high voltage system. So here we'll have new master boards, which will include all the CSCs. And in LS3, like I mentioned earlier, we'll have new data motherboards, which will replace the copper version. So it's a copper data motherboard, which will have new optical links. So this is an optical data motherboard. So these will be based on Kintex ultra-scale FPGAs, which can transmit data up to 30 gigabits per second. And then also in LS3 is the upgrade of the front-end driver. So this is part of the data acquisition system, where you have new ATCA boards, which provides a ton of data, nearly 600 gigabits of data per second to the CSC data acquisition system. So a lot of electronics will be upgraded. So on this slide, a few pictures how this is done. So basically in the cavern, chambers are extracted with a crane, and then they're hoisted up or transported up rather to SX5, which is at the surface. And in a dedicated CSC lab, these chambers are tested. Well, they're refurbished and tested, and a crew of about 20 people are involved in this refurbishment. So the status where we are now. So there are 4 distinct work streams. 3 out of 4 were just completed before the outbreak of COVID-19. The 4th one was just about to begin. Then CERN shut down in mid-March, was shut down until early June. And then as CERN is starting up again, the last stream, which is the refurbishment of the negative side of CSC, the inner ring chambers. So that will be starting up again. And that schedule has been shifted by 2.5 months, but also extended by 2 months. So at the moment, I think they're reinstalling the ME-2 one side of the CSEs. So in a kind of a status of this is shown below, where you have different colors for what kind of phase they're in for every single station. I'd like to also say a few words about the irradiation longevity studies. So as I explained, with the upgrade of the upgrade of the LHC to the HL-LHC, we'll have a lot more radiation that will be exposed to. So it's important to have electronic components that are able to withstand this intense radiation, in particular for the onboard electronics in the inner ring chambers. So you need radiation tolerant optical transceivers, memory units, and all, etc. And so there are 4 distinct testing sites, both at CERN, at Texas A&M, and at UC Davis, where components are tested for hadrons, protons, neutrons, photons, and again, for protons at the UC Davis cyclotron. And so each component receives a dose up to about 30 kilorats, which is 3 times the HL-LHC exposure. And so typically the single event upsets are counted, which are bit flips caused by ionizing radiation, and the electronics dead time is tracked during beam exposure. And so an example of a pretty recent test. So the picture on the right shows a radiation test board of an ODMB. So that's a data motherboard, EEPROM. So it's a memory board for the data motherboards. So this was tested at time of cyclotron on protons. And so these tests are ongoing. And then one final thing about gas mixture studies before I close my presentation. As I explained before, there's the CSC electronics upgrade. There's the connection with GEM detectors, but there's also a requirement from you that restrict usage of greenhouse gases. So namely CF4, which is a 10% component in the CC gas mixture, which is used as an anti-aging additive. That needs to be ultimately removed from the gas mixture or replaced with something more suitable. And so alternative gas mixtures are being investigated at CERN using a prototype CSC. And so a picture of that prototype is shown at the top right there, where you can see a box of 30 by 30 centimeters squared. It has 2 gas caps with standard CSC electronics and data acquisition systems. So you can test different gases and read out the data and do a count rate analysis, for instance. And so these studies have a two-fold approach. One is you test the longevity of these chambers with gases with less CF4. For instance, you drop it from 10% to about 2% in steps of 2%, and you test and you do several tests where you plot the count rate versus the high voltage, for instance. Another thing that is being done is where CF4 is swapped out by more environmentally friendly gases. For instance, this HFO gas, which has a similar turn on and a similar plateau as the CF4 gas. So that's also being done, and that looks quite promising. So it'd be interesting to see what the studies will reveal. So I think that's about it for this presentation. Just a quick update on the CSCs. So that brings me to my summary. So the CSC system will be upgraded for the HL-LHC during LS2, but also LS3. It's a pretty extensive upgrade program, 1,400 new electronics boards, new algorithms that we interface with a GEM system, new gas mixtures and stuff. This operation is currently ongoing. So 3 work streams were completed. The 4th one is being completed now, or at the moment. So with CERN opening up again, this 4th stream is ongoing. And then also ongoing are the irradiation and alternative gas mixture studies. Okay, so that's about it. Thank you very much.
Thank you, Sven. Very nice talk. Other questions for Sven? If not, I was wondering for the gas, the CF4, does it have to be completely eliminated, or can we keep a little bit?
Right, I think so. Yeah, that's my understanding, at least, that it needs to be completely eliminated.
All right. And then I was wondering, so when you're bringing the chambers up to the surface, do you have to deal with activation, or do you already waited several months and it's not an issue?
Right. I think at this point that the chambers are quite inactive, having not been irradiated since end of 2018.
Right. Okay. Good. Thanks. Then we can move maybe to the last talk. Last but not least is Xueye Hu from the University of Michigan.
Yes.
Talking about the upgrade of the ATLAS Muon Drift Tube front-end electronics.
Yeah. Hi. Let me share my screen. Could you see it?
Yes, very good.
Okay. Okay. Hi everyone. My name is Xueye. So today I will give a talk about the upgrade of the ATLAS Muon Drift Tube front-end electronics for high luminosity LHC runs. Okay. Next page. Here's today's outline, 4 parts, and I'm gonna start with a very brief introduction of ATLAS Muon spectrometer. So for muon spectrometer, it is responsible for triggering, identification, and the momentum measurement of the muons. It has about 4 sub detectors. So the residual plant chamber, RPCs, and the thin gap chambers, TGCs, are used as primary trigger detectors. The monitored drift tubes, MDTs, and the cathode strip chamber, CSCs, are used as precision trackers. So during the high luminosity LHC runs, the MDT detector need to be upgraded to first improve the muon PT resolution at level 0 triggering, and second, we'll need to cope with high rates. And under this condition, the MDT readout electronic system must be upgraded too. Okay, moving forward. So I show you both current system and the future upgrade system. For the current system, the MDT and the trigger chambers are read out independently. So MDT readout only rely on level 1 trigger. So this allows the system works with a lower bandwidth. And the trigger mode used at the front and the part. And for the future, the high luminosity runs, MDT data will need to use sharpen the trigger decisions. So first we'll need to find accurate PT using the raw seed from the trigger chambers and confirm or reject trigger hypothesis. And second, the triggerless mode was used at the front end. So we move the track fitting into the counting room. So this requires system to have a higher bandwidth. So this is a general picture of the future system. I will walk through this one by one in this slide. Okay, so as you can see, there are 3 parts. So first is MDT detector. So second, the front electronics, which is the main topics today. And the last one is the back-end electronics. So for the front end part, first you see the meddling card. It needs a new SD and a new TDC to working with the triggerless operation and a higher bandwidth. So eventually there will be 80K SDs and 22K TDCs produced and delivered. So of course, we will need new mezzanines too. So after that, you will see the CSM. This will need to be upgraded too. So the new CSM will based on the CERN GBT chipset. So it will need flexible handle both old and new mezzanines. And this will need to be a fixed latency. And for the bandwidth is up to 20 gigabit per second. So eventually it will deliver about 1.2K boards. And for the last part, the backend MDT data processor, it will provide MDT trigger candidate to the global L0 trigger level, and it will have the precision data readout, and eventually it will deliver 64 boards based on ATCA standard. Okay, moving forward. Second part. Okay, for the front electronics upgrade, I will start with the SD, which is amplifier shape discriminator. So SD have 8 channels. It's based on GlobalFoundries 130 CMOS process. It has 4 key parts: the preamplifier, shaper, Wixon ADC discriminator, and the last one, up the driver. So in a short summary, the SD has 2 modes, as you can see, marked here. So the first one on the top, it just measures the threshold crossing. And the second mode, it will measure the integrated charge about 15 nanoseconds and send it out. Okay, moving forward. So the current SD project status, so detailed study performed and no design problem found. So test up SD up to 1 megarad, and a lot of chip behaviors are checked. So we didn't feel the big difference before and after the irradiation. Also, the SD performance are studied at GIF++ with 150 GeV muon beam. In the lower picture on the left, you can see the SD drift time is about 750 nanoseconds. And this one just shows you the position resolution of a single tube measured by SD. So it actually compared to the current or legacy SD, to get a little bit improved, 95 micro. Okay. So second part with the TDC, it's time digital converter. So for the TDC, it has 24 channels input, 2 channels output, working at 320 megabit per second. It also has 4 key parts: the EPLL, the timing circuits, included the cost time and fine time measurement, and the bin size is about 0.78 nanosecond. And also the third part, the TDC logic. It includes the triggerless or trigger mode, or it needs to support the new output protocol and have the high-speed interface. And for the interface part, it has the serial output, the configuration interface, and the clocks. So you can see the yellow blocks marked here. These are the blocks with TMR, trigger modular redundancy, implemented. Here it just shows you a general picture of the TDC ASIC layout. Okay, so for the current TDC project status, detailed study performed and no design problem found. On this photo, on this picture, it just shows you the bin size of all 48 channels. So the variation is less than plus minus 40 picosecond. And for the latency measurement, we have 400 kilohertz hit rate, and 99% of the data was read out after 350 nanoseconds. And here just show you a brief history of the TDC development. So it started in 2016, the version 0, and now we have version 2 submitted, fabricated, and tested. So the main change implemented in version 2 is triple module redundancy and use the new BGA package. So coming to the mezzanine card, this is mainly the platform for both SD and the TDC ASICs. So for the design, it need to be compatible with the legacy mezzanines. So for example, like dimensions and locations of the connectors, and also pin assignment. So this mezzanine card, of course, need to be radiation tolerant. So all critical components must be radiation tolerant. And the we have commercial LDO used on board. So the radiation tests have been scheduled. And you can see on the left corner, these 3 different mezzanine cards. This is just a combination of multiple SD versions and TDC versions, basically for the demonstration purpose. And on the right picture just show you all the mezzanine cards based on the new latest version of SD and TDCs, and will be used in the next test. So they passed the preliminary design review in March 2020 this year. Okay, coming to the CSM, the chamber service module. So for the CSM, the bandwidth need to handle the inputs up to 36 channels times 320 megabit per second. For the output, the uplink fiber bandwidth is about 20 gigabit per second, and the downlink is about 2.56 gigabit per second. It also have 4 key parts. So for the LPGBT, it's almost the key of the key. So it has two LPGBT chips working in master level mode. So it works as a big multiplexer of the information of data and monitoring information in the uplink direction. It also needs to distribute the clocks and the configuration information from the downlink side. And for the GPTSCA, it's mainly just for monitoring and the configuration, the JTAG mode. And for the found IPGA, it just receives the TTC information and fan out to all the 18 mezzanine cards in the front. And the last one is the VL plus optical module, just to convert the signal from electronics to optics and send over the fiber to the backend. Okay. The current CSM project status. So we have prototype version 1 passed the standalone test and different integration tests, and shown the picture here. And also version 2 design shown on the right corner. The design was submitted in July this year. And also I also show a test result example in the next slide of the middle setup. As you can see in the picture, the CSM version 1 tested with up to 6 mezzanines, and we on purpose disconnect one mezzanine just to simulate the possible case we may encounter during the real operation, so like maybe some mezzanine card just broken. So we do not want these broken mezzanines interfere with other mezzanines in the same chain. So we show the result here. So we still can successfully receive 5 mezzanines test result, and the configuration also can be done properly. The data decoded here, showing the data chain also working as we expected. Okay. So the third part, our integration test plan. So for the current activities, we build a SMDT cosmic ray test system. As you can see in the picture, we have legacy electronics used mainly to test these SMDT new chambers and have a working system so that we can replace the legacy electronics by the new electronics one by one step. And you can see this time spectrum are measured as we expected. Okay. Our general integration test goal was to integrate different electronic components together and perform studies with without SMDT or MDT chambers and the L0 MDT trigger processor. So we plan to perform these integration tests step by step, and the first step already done. So in the next, we will work with SD, with TDC version 2 and the CSM version 2 without chambers, and we'll develop a mini DIQ system for integration test. And then we will integrate L0 MDT demonstrators. And finally, we want to have all final versions of SD, TDC, CSM, and the L0 MDT version 1 in a full chain. Okay, that's almost to the end. So here is today's summary. So to cope with high rates and improve PT resolution, we need to upgrade all MDT electronic system. And the MDT front-end upgrade project has made a lot of progress and passed major reviews like SPR, FDR, and PDR. So SD is currently already in production run. For TDC, it's close to the final designs. And for the mezzanine card and the CSM prototype version 2, it has all final features. And we have an ongoing development on the front-end electronics integration. So basically, we want to have a full chain. We call it mini DIQ, started with from chamber to mezzanine card to CSM and to L0 MDT emulator. And he also listed the general schedules of 4 different projects. So basically, it's very promising, and we are on track. So thanks. That's it.
Okay, great. Thank you very much. Are there any questions? I don't see anything. So I guess you're not planning on any staggered installation like in CMS, right? It will be all going in LS3?
Yes.
Okay. Because some, like the ASD is relatively early. Okay, I don't see any hands up. So I would like to thank all the speakers again of today's session. The organizers are foreseeing this extra hour at the end now for free form discussion, if you wish. Since we are not such a large group, we're proposing to merge with track number 12, which is the current detectors. And so in 15 minutes, 8:45 CERN time, if you want to join that, join the Zoom room of track number 12. And otherwise, join the next session of the upgrades tomorrow. All right, and I wish you a great rest of the conference. Bye-bye.
Bye.
Thank you. Bye.
Bye-bye.